Hello again, and welcome back to this quiet corner where curiosity slows down and science takes its time. Tonight we're asking a question that sounds simple, but is anything but. When physicists talk about nothing, what do they actually mean? At first glance, it might sound straightforward. Nothing should mean empty space. No matter, no stars, no galaxies, no air, no atoms, just emptiness. But the deeper you go, the less clear that picture becomes. Physics has a way of turning what seems obvious into something far stranger than we first imagined. Think of an ordinary room. If you carefully remove all the furniture, take away the chairs, the shelves, the curtains, even the dust, you might look around and say the room is empty. That feels like nothing. But in physics, that room is far from empty. Light still passes through it. The walls still radiate heat. Even if you sealed it tight and pumped out every last molecule of air, reducing the pressure to nearly zero, the emptiness would not be absolute. Photons could still leak in from outside. The walls themselves, built of atoms, would quietly vibrate, releasing tiny bits of energy. So even when you think you've got rid of everything, something remains. This is where physicists get picky about language. For everyday conversation, nothing can mean an empty box, an unused drawer, a space with nothing obvious inside. But physics demands more precision. If you want to describe the very beginning of the universe, or understand whether it could have come from nothing, you need to know exactly what that word implies. Because in physics, nothing is never quite so simple. One of the first distinctions to make is between philosophical nothing and physical nothing. Philosophical nothing is the absolute absence of everything. No space, no time, no laws of physics, no potential for anything at all. Pure non-existence. It's the kind of nothing people wrestle with when they ask why there is something instead of nothing. Physics rarely talks about this version, because it's not clear how you could study or measure it. Physical nothing, on the other hand, usually refers to a vacuum, the closest thing to emptiness you can create within the framework of science. So what is a vacuum? Early scientists thought of it as a simple void. Aristotle argued that nature abhors a vacuum, claiming true emptiness could never exist. Centuries later, experiments proved that you could in fact pump air out of a chamber and create a near-perfect vacuum. Galileo and Torricelli showed that suction, barometers, and pumps all relied on creating spaces with very low pressure. From there, physics slowly refined the concept, but even in modern laboratories, a vacuum is not perfectly empty. At best, it's a space with extremely few particles. That is still something. And then quantum mechanics came along, making the picture even stranger. According to quantum field theory, what we call empty space is filled with fields that stretch across the universe. Even if you remove every particle, the fields remain. They cannot be switched off. They are woven into the fabric of reality. And because of the uncertainty principle, those fields are never completely still. They fluctuate, jitter, produce pairs of particles that pop into existence and then vanish almost instantly. These are called quantum fluctuations. They are not directly visible, but they have real effects. For example, they shift the energy levels of atoms, a phenomenon measured with exquisite precision in laboratories. This means that even in what we call a perfect vacuum, activity is bubbling away beneath the surface. So when a physicist says nothing, they usually mean the quantum vacuum, a state with no particles, no radiation, but with fields and fluctuations that can never be removed. That is very different from the ordinary idea of nothing. It's more accurate to say that in physics there is no such thing as absolute emptiness. What you have instead is the lowest possible energy state of the universe, and even that is restless. This distinction becomes important when people ask whether the universe could come from nothing. If by nothing you mean the quantum vacuum, then physics has ideas about how energy could fluctuate, how space-time could expand, how particles could emerge. If by nothing you mean absolute philosophical non-existence, then science has far less to say. because you need at least some framework of rules for physics to operate at all. Without time, without space, without laws, there is nothing to describe. It's tempting to blur these two meanings, but scientists are careful not to. Some theories suggest that the universe could emerge from a quantum vacuum through processes allowed by the laws of physics, but that's not quite the same as saying it came from nothing in the everyday sense. The vacuum is a kind of something, even if it looks like emptiness to us. To see how deep this goes, imagine zooming in on what seems like empty space. Not with your eyes, but with the mathematics of physics. You would find fields everywhere. The electromagnetic field, the Higgs field, others that carry the forces of nature. They interact, ripple, and sometimes condense. These fields give particles their masses, govern their interactions, and under the right conditions produce dramatic events. In the early universe, fields shaped the expansion of space itself. The vacuum is not a blank canvas. It is more like a stage filled with invisible machinery, always ready to bring actors into being. And then there is energy. In many cosmological models, the total energy of the universe might be zero. Matter and radiation carry positive energy. Gravity, strangely, can carry negative energy. Add them together, and it's possible that they cancel out. This leads to the idea of a zero-energy universe, where existence does not violate conservation laws because, in a sense, the ledger balances perfectly. If that is true, the universe did not need an external supply of energy to get started. It could have begun as a fluctuation, a tiny deviation from nothing that inflated into the cosmos we see today. Of course, these ideas remain deeply challenging. They are supported by mathematics, by observations of cosmic expansion, by measurements of the microwave background. But the leap from quantum fluctuations to galaxies, from jittering fields to stars and planets, is vast. Scientists fill in the story step by step, testing predictions, refining models, searching for subtle signatures in the sky. Yet even with all that, the word nothing continues to cause confusion. To a physicist, it means one thing. To most people, it means another. It helps to think of nothing as a spectrum. On one end, you have the ordinary emptiness of a vacuum chamber, a space cleared of atoms. In the middle, you have the quantum vacuum, filled with fluctuating fields. On the far end, you have philosophical nothing, the absence of existence itself. Physics comfortably handles the first two. The third lies outside its reach, at least for now. When cosmologists describe the beginning of the universe, they tend to stay within the boundaries of physical nothing. They ask what the earliest state of spacetime was, how quantum fluctuations behaved, what inflation could have done, how the laws of physics operated at extreme energies. They do not claim to explain why there is something rather than nothing in the deepest sense. That question, at least today, remains a mystery, but perhaps the two are not entirely separate. Every time physics pushes deeper, it redefines what nothing means. What once seemed like empty space turned out to be full of atoms. When atoms were stripped away, fields remained. When fields are examined closely, fluctuations appear. Perhaps nothing is not a final concept, but a horizon that moves as our understanding grows. Each step shows that emptiness is less empty than we thought, and that leaves us with a peculiar situation. When we ask if the universe came from nothing, we need to ask which nothing we mean. The ordinary emptiness of space, the restless vacuum of quantum fields, or the absolute philosophical void, each carries different implications, each requires a different kind of answer, and each shows how slippery the idea of nothing really is when examined through the lens of science. So what physicists mean by nothing is not absence in the absolute sense. It is a ground state, a field-filled stage, an arena that still holds potential and activity. It is not the end of explanation, but the beginning. From this strange version of nothing, the next questions unfold. How could a fluctuation trigger expansion? How could the laws of physics operate before space-time itself existed? what does it mean for time to have a beginning? When we speak of emptiness in physics, we never really mean stillness. What seems to be the quietest, barest stage possible is in fact humming with activity at scales too small for us to sense directly. This is where the idea of vacuum energy enters the story. It is one of the most counterintuitive discoveries of modern science because it tells us that the vacuum, the thing we call nothing, actually holds an energy of its own. And that energy is not only measurable, it may be responsible for shaping the largest features of the universe itself. To appreciate this, it helps to remember what quantum mechanics did to the picture of nature. Before it arrived, the vacuum was simply a void. You might imagine it as an infinite canvas with no paint, no texture and no depth. After quantum mechanics, that image collapsed. Suddenly, the vacuum became something far richer, a medium filled with restless possibility. Fields are never silent. According to the uncertainty principle, they must fluctuate. The rule that forbids us from knowing both the exact position and exact momentum of a particle also forbids a field from being perfectly calm. A perfectly calm field would mean zero uncertainty, and quantum mechanics will not allow that. So fluctuations are built into the foundations of reality. One way to picture it is to imagine a calm-looking pond. On the surface, it may appear flat and still, but beneath molecules are always jostling, colliding and moving. You cannot have absolute stillness because temperature, energy and random motion never quite reach zero. Quantum fields behave in a somewhat similar way. Even at their lowest energy state, they jitter. These jitters produce what we call virtual particles, pairs that flicker into being and disappear again in unimaginably small fractions of a second. They are called virtual because they never persist long enough to be observed directly, but their effects can be detected. One of the first clear demonstrations of this came in the Casimir effect. Imagine placing two uncharged, parallel metal plates very close together in a vacuum. Classical physics would predict that nothing unusual should happen. But quantum physics says otherwise. The plates restrict which fluctuations can exist between them. Only certain wavelengths fit in the gap. Outside the plates, all wavelengths are possible. The result is a pressure difference, with more fluctuations outside than inside, and this pushes the plates toward each other. The Casimir effect has been measured in laboratories with exquisite precision, confirming that vacuum fluctuations are not just a mathematical trick. They are real, and they exert forces. This leads directly to the concept of vacuum energy. If the vacuum is always fluctuating, then it must contain energy. Not in the form of matter or radiation, but in the form of fields refusing to be perfectly still. Calculations show that the amount of this energy could be enormous. In fact, naive estimates from quantum field theory suggest a value far larger than anything observed in the universe. Reconciling this with cosmology is one of the deepest puzzles in physics, often called the cosmological constant problem. The universe does contain vacuum energy, and we see its effects in the accelerated expansion of space, but the measured amount is tiny compared to the predictions. Why that mismatch exists remains an unsolved mystery. Yet the existence of vacuum energy is not in doubt. In 1998, observations of distant supernovae revealed that the expansion of the universe is speeding up, not slowing down as expected. The simplest explanation is that space itself carries energy that counteracts gravity on cosmic scales. This is now called dark energy, and one candidate for what it might be is simply the vacuum energy predicted by quantum mechanics. If so, then the energy of nothing is driving the fate of everything. The implications are staggering. What seems like empty space is not just a passive background. It has properties. It can push the universe apart. It can dictate how galaxies drift, how structures form, how the cosmos will evolve over billions of years. The largest scale dynamics of reality are being guided by the smallest, most invisible fluctuations. But even at more modest scales, vacuum fluctuations leave fingerprints. In atomic physics, the Lamb shift, a tiny change in the energy levels of hydrogen, is caused by the interaction between the electron and the fluctuating vacuum. Experiments measuring magnetic properties of particles also show the influence of these ever-present fluctuations. Each of these effects confirms that what we call empty space is actually alive with hidden activity. The term virtual particle sometimes causes confusion. It suggests that particles are literally appearing and disappearing, popping in and out of existence. In truth, it is better to think of them as temporary excitations of the field. They are not particles in the sense of being independently observable things. Instead, they are a way of describing how the field responds when probed. For example, two charged particles approaching each other can exchange a virtual photon, producing the electromagnetic force between them. That photon is not observed directly, but its presence is inferred from the effect it has. In this sense, the vacuum is a medium through which interactions occur, not a simple void. This has led some physicists to describe the quantum vacuum as a kind of stage filled with invisible scaffolding. Fields pervade it, fluctuations stir within it, and from this restless environment, all known particles and forces emerge. The Higgs field, for instance, permeates the vacuum and endows particles with mass. Without it, quarks and electrons would be massless, atoms would not form, chemistry would be impossible. The fact that we exist at all depends on the structure of the vacuum. The vacuum is not unique either. In quantum field theory, different possible vacuum states exist, each corresponding to different arrangements of fields. Our universe seems to occupy one particular vacuum, but in principle, others could be possible. This leads to speculation about whether the universe could transition from one vacuum state to another. Such a transition is called vacuum decay, and while it is not something to lose sleep over, the possibility shows again how nothing in physics is a far more complex concept than it appears. When cosmologists ask how the universe could arise from nothing, they often have this picture in mind. A vacuum filled with fluctuations governed by quantum laws, able under certain conditions to generate particles, energy, and even space-time itself. It is not nothing in the absolute sense, but it is the closest thing physics can offer to a natural starting point. What makes this even more fascinating is the scale of influence. At the microscopic level, fluctuations shift energy levels of atoms. At the cosmic level, vacuum energy drives the expansion of the universe. Across all scales, what we thought was nothing proves to be essential. This is why modern physics is so cautious with words. Nothing is never really nothing. A vacuum is never truly empty. Space is not a backdrop but an active player in the unfolding of reality. And the fluctuations that ripple through it are not imperfections but fundamental features. As we follow this trail further, the questions only deepen. If the vacuum has energy, why is its value so small compared to predictions? Could different regions of space have different vacuum energies, leading to different physical laws? If fluctuations concede the formation of galaxies, what does that say about the role of randomness in creating structure? And if vacuum energy drives cosmic acceleration, what does that mean for the long-term future of the universe? Each of these questions shows that studying nothing leads us directly into the heart of the most profound mysteries of cosmology. It links the smallest scales of quantum physics with the largest scales of astronomy. It tells us that emptiness is not a blank page, but the ink itself, always there, even when we don't notice it. It is easy to imagine that if you strip the universe down to its bare minimum, take away every planet, every star, every atom, and every particle of light, you would be left with nothing at all. An empty canvas, quiet, featureless, and completely still. For centuries, that was the picture people carried in their minds when they thought of the void. But the closer physics has looked, the more that picture has dissolved. What appears to be empty space is anything but. The quantum vacuum is not empty. It is a restless medium filled with hidden structure, activity, and potential. To understand why this matters, it helps to recall how physics describes reality at its most basic. Every particle, every force, every interaction is represented not as an isolated object, but as part of a field that extends through all of space. Electrons belong to the electron field, photons to the electromagnetic field, quarks to their own fields, and so on. These fields are not confined to particular places. They exist everywhere, filling every region of the universe. Even when there are no actual particles present, the fields remain. In the classical world, you might picture a field as a calm surface, smooth and featureless until something disturbs it. A stone tossed into a pond produces ripples, but without the stone the surface lies still. Quantum physics does not allow that kind of absolute stillness. Because of the uncertainty principle, fields cannot sit in a perfectly stable state. They must fluctuate. At every point in space, tiny jitters occur, giving rise to brief appearances of energy, particles, and disturbances. These fluctuations are unavoidable, as fundamental to the fabric of reality as gravity itself. What this means is that the vacuum, far from being empty, is alive with activity. For unimaginably short intervals, particles and antiparticles emerge from the vacuum, borrow a bit of energy, and then annihilate each other, returning that energy back. This happens constantly, everywhere, with no pause. The scale of time involved is so brief that these particles cannot be directly observed. They are called virtual, not because they are unreal, but because they exist outside the boundaries of what can be detected as persistent matter. Yet their influence is measurable. They shift atomic energy levels, modify particle interactions, and in some cases generate forces that can be measured in the laboratory. One of the most striking examples is the effect on the hydrogen atom. According to simple quantum mechanics, the electron orbits around the nucleus with specific energy levels. But when you account for the jittering of the vacuum, those levels shift slightly. The electron interacts not only with the nucleus, but also with the cloud of virtual particles flickering in and out of existence. The correction is tiny but real, and it matches experimental measurements to astonishing precision. That match is one of the reasons physicists are so confident that the vacuum is not empty. It has a structure, and that structure matters. Another demonstration comes from the force between two uncharged metal plates placed very close together. Classical reasoning says there should be no force at all, yet experiments show that the plates attract. The explanation lies in the vacuum fluctuations. Between the plates, only certain wavelengths of fluctuations can exist. Outside the plates, all wavelengths are possible. This imbalance creates a pressure difference that pushes the plates together. It is subtle, but it has been measured and confirmed. What seems like a void between the plates is in fact a seething environment, and its properties can push matter around. On the larger scales, the presence of vacuum energy becomes even more dramatic. When astronomers discovered that the expansion of the universe is accelerating, the simplest explanation was that space itself carries energy. This energy acts like a pressure that drives galaxies apart. In other words, the quantum vacuum, which seems like empty space, has enough energy to influence the fate of the entire cosmos. Without it, the expansion might slow down or even reverse. With it, space keeps stretching faster and faster, shaping the long-term destiny of the universe. It is worth pausing on how strange this is. Something we once thought of as nothing turns out to contain the seeds of everything. The vacuum underlies the existence of particles, the forces between them, and even the large-scale structure of the universe. It is the foundation, not the absence, of reality. There is another layer to this story, one that comes from the Higgs field. This field pervades the vacuum, and its presence is what gives mass to fundamental particles. Without the Higgs field, electrons and quarks would have no mass, atoms would not form, chemistry would not happen, and stars could not shine. The very existence of matter as we know it depends on the vacuum being structured in just this way. That is why the discovery of the Higgs boson in 2012 was so important. It confirmed that the vacuum is not featureless but shaped by a field that affects every particle in the universe. Physicists sometimes talk about the vacuum as if it has a kind of personality. In one state, it may behave in one way. In another, it may behave differently. These are called vacuum states, and the universe we live in occupies one of them. But the equations allow for other possible vacua with different properties and different laws of physics. If the universe were to shift into another vacuum state, everything we know could change. Masses, charges, and forces might alter. Structures might dissolve. Fortunately, if such a transition is possible, it is likely unimaginably rare on human timescales. Still, the possibility shows again that the vacuum is not empty. It is a medium with properties, with a history, and perhaps with a future of its own. Even black holes tell us something about the fullness of the vacuum. According to Stephen Hawking, black holes are not completely black. They radiate very faintly because of quantum effects near the event horizon. Virtual particle pairs appear, and under the extreme conditions of curved space-time, one particle can fall in while the other escapes. The escaping particle becomes real, carrying energy away. Over vast spans of time, this radiation can cause a black hole to evaporate. This process, called Hawking radiation, depends entirely on the fact that the vacuum is not empty. Without fluctuations, no such radiation would exist. This idea stretches to the very origin of the cosmos. Some cosmological models suggest that the universe itself may have arisen from a fluctuation in the vacuum. In such scenarios, space and time themselves are not pre-existing containers, but phenomena that emerge from the restless structure of the vacuum. A small fluctuation, allowed by quantum mechanics, could have expanded, inflated, and grown into everything we see today. Whether this picture is complete remains uncertain, but it illustrates the central role the vacuum plays in our understanding of beginnings. When you hear physicists say that the vacuum is full, they mean it is full of fields, of fluctuations, of possibilities. It is not an empty stage waiting to be used. It is an active environment shaping the performance before the actors even arrive. It determines what kinds of particles can exist, how they interact, and how structures form. It carries energy that pushes galaxies apart and whispers through the smallest details of atomic spectra. And this raises questions that go to the heart of physics. Why does the vacuum have the properties it does? Why is the energy of the vacuum so small compared to what theory suggests? Could the universe exist with a different vacuum? And if so, what would it look like? Are we living in the only possible vacuum, or is ours just one among many? These are not just abstract speculations. They guide experiments, drive observations, and inspire new theories. Every step taken to understand the vacuum has led to new insights, and often new mysteries. So when you think of empty space, imagine not a silent void, but a restless sea. Invisible fields ripple through it. Virtual particles appear and vanish. Energy hides in its structure. From this sea arises the matter in your body, the light from distant stars, the expansion of the cosmos itself. The vacuum is not nothing. It is, in its own way, everything. When you think about particles, you probably imagine them as the tiny building blocks of matter, the little bricks from which the universe is constructed. Electrons circling nuclei, photons carrying light, quarks binding into protons and neutrons. In that sense, particles feel solid and real, the basic actors on the stage of physics. But quantum theory forces us to expand that picture, because not all particles are the same. Some exist in the ordinary way, with measurable mass and charge, travelling through space, colliding and leaving traces in detectors. Others exist only fleetingly, never long enough to be directly observed, but still influencing the play around them. These are virtual particles, and they form one of the most fascinating parts of modern physics. The name alone can be misleading. virtual does not mean fake. It simply means that these particles do not satisfy the same rules as the ones we can measure directly. When two electrons repel each other, for example, the electromagnetic force that pushes them apart can be described as the exchange of a virtual photon. That photon is not seen, not detected, and not bound by the usual relationship between energy, momentum, and mass. Yet without it, the force would not exist. So the virtual particle is the bookkeeping entry that makes the interaction work. This idea emerges naturally from quantum field theory, which describes every particle as an excitation of a field. When fields interact, they do so through exchanges, and those exchanges can be represented as particles appearing and disappearing in the middle of the process. They are not there before or after, but they shape the outcome. If you look at a diagram of such an interaction, the lines inside, the ones that begin and end without extending to the outside world, those represent virtual particles. One of the most striking things about this framework is how successful it has been. The calculations that use virtual particles give answers that match experiments to incredible precision. Predictions about the magnetic properties of the electron, for example, rely heavily on the presence of virtual particles, and the agreement with measurements is one of the best in all of science. That level of accuracy tells us that, however strange they sound, virtual particles are an essential part of the description of reality. But what does it mean, physically, to say that space is filled with such things? If you were to zoom into the vacuum at the smallest scales, you would find constant activity. Virtual pairs of particles and antiparticles flicker into being, borrowing energy from the vacuum, then annihilating each other and disappearing again. They do this within time intervals so short that the borrowed energy does not violate the conservation laws thanks to the uncertainty principle. The result is a restless sea, a background froth that never settles. One of the simplest ways to see the effect of this sea is to look at how forces behave. The strength of a force depends on how many virtual particles contribute to the interaction. For instance, when a charged particle is placed in space, it polarizes the vacuum around it. Virtual particle pairs, some carrying charge, briefly appear and align with the field. This cloud of activity modifies the effective charge seen at a distance. In this sense, the charge of an electron is not a fixed property, but a number that depends on how the surrounding vacuum responds. The electron is dressed by virtual particles, and that dressing affects how it interacts with the world. This is more than a curiosity. It has measurable consequences in particle accelerators, where scattering experiments probe the structure of forces at very high energies. The results confirm that what we call the fundamental constants of nature are not truly constant. They run with energy, shifting because of the contributions of virtual particles at different scales. This is known as renormalization, and it is one of the triumphs of quantum field theory. Without the sea of virtual particles, the whole structure would collapse. The sea shows up again in nuclear physics. The strong force that binds quarks together into protons and neutrons is mediated by particles called gluons. These too can give rise to virtual pairs that influence the binding energy of the system. The dynamics of quarks and gluons are so complicated that they can only be calculated with powerful computers, but the role of virtual particles is always present. Even the mass of the proton, one of the most basic ingredients of matter, is not simply the sum of the masses of its constituent quarks. Most of it arises from the energy stored in the sea of gluons and virtual pairs inside. In other words, the solidity of matter, the weight of the stuff we touch, owes its existence to the activity of particles that do not exist in the usual sense. The phenomenon also extends to empty space near massive objects. Around a black hole, the intense curvature of space-time affects how virtual pairs behave. Normally they appear and disappear together, but at the event horizon, one can fall in while the other escapes. The escaping particle becomes real, carrying energy away as radiation. This is Hawking radiation, and it suggests that even the darkest, most inescapable regions of the cosmos are connected to the restless sea of virtual particles. Over unimaginably long times, this slow leak could evaporate a black hole entirely. And there are even more dramatic possibilities. Some cosmological models suggest that the entire universe could originate from a fluctuation in the vacuum. In this view, the sea of virtual particles is not just a detail of interactions, but the source of existence itself. If space and time can emerge from quantum processes, then the restless sea is not a background but a cradle, holding the potential for entire universes. Whether this is literally true remains unknown, but the idea underscores how central the concept of virtual particles has become. It can feel unsettling to think that everything around us, every stable particle and every durable structure, rests on a foundation of things that flicker in and out of being. But perhaps the distinction between real and virtual is not as sharp as it seems. After all, what makes a particle real is that we can detect it, measure it, and follow it across time. What makes a virtual particle virtual is that it never quite lasts long enough. Yet both come from the same fields, both obey the same rules, and both contribute to the physics we observe. The sea of possibilities is not separate from reality. It is reality, expressed in a form we cannot perceive directly. As experiments continue, the evidence for this picture only deepens. High-energy collisions in particle accelerators create showers of new particles, many of which emerge from the activity of virtual pairs. Precision measurements of atomic spectra show shifts that can only be explained by the influence of the vacuum sea. The magnetic moment of the muon, recently measured to greater accuracy, may even reveal new layers of virtual contributions beyond the known particles of the standard model. Each of these discoveries reminds us that what we call empty space is a dynamic participant in the universe. And so, when physicists talk about the vacuum as a sea of possibilities, they are not being metaphorical. They are describing a literal framework in which fluctuations, exchanges, and transient excitations shape the world we see. From the repulsion of electrons to the evaporation of black holes, from the mass of protons to the expansion of the universe, virtual particles play their part. They may not be real in the everyday sense, but they are indispensable to the story. This understanding carries us forward, because if the vacuum is a sea, then the question becomes what happens when that sea is disturbed on cosmic scales. How do the fluctuations ripple out, and how could they seed the structures that later became galaxies and stars? When physicists talk about space and time, they no longer treat them as separate things. In the early 20th century, Albert Einstein's theory of relativity changed that forever. Instead of space being one stage and time being another, relativity merges them into a single fabric called space-time. This fabric is not static. It bends, it stretches, and it responds to matter and energy. The picture is not one of objects moving through a rigid background, but of the background itself participating in the motion. To say that space-time is dynamic is to say that the universe is not merely filled with structures, but is itself a structure that changes. This idea is so ingrained now that it can be difficult to remember how radical it once was. Before relativity, Isaac Newton's physics imagined time as an absolute flow, steady and universal, and space as an unchanging stage where the events of the universe unfolded. Matter moved, forces acted, but the stage remained untouched. Einstein shattered that assumption. He showed that time runs at different rates depending on motion and gravity, and that space is not rigid but curves in response to mass and energy. The result is a universe in which geometry itself is dynamic. Think of the Earth orbiting the Sun. Newton would say the Sun exerts a gravitational force that pulls the Earth inward, balanced by the Earth's motion, so that it keeps circling rather than falling. Einstein reframed it. He described the Sun as curving the fabric of space-time around it, and the Earth as following a path within that curved geometry. There is no invisible tether pulling the Earth. Instead, the Earth moves along the curves that space-time provides. Gravity, in this picture, is not a force but a feature of geometry. This way of thinking explains why light, which has no mass, is also affected by gravity. During a solar eclipse in 1919, astronomers observed starlight bending around the Sun. Newton's gravity could not easily account for this, but Einstein's curved space-time predicted it precisely. That experiment was one of the first dramatic confirmations of relativity, and it showed that even something as intangible as a beam of light is bound by the structure of space-time. But calling space-time a fabric is not just a metaphor. It is an attempt to capture how it behaves. Like fabric, it can stretch under tension. Galaxies move apart because space-time itself expands, carrying them with it. Like fabric, it can ripple when disturbed. When massive objects accelerate, such as black holes colliding, they send gravitational waves across the cosmos. These ripples in space-time were detected directly for the first time in 2015, a century after Einstein predicted them. The signal matched what theory expected, confirming again that space-time is not static, but alive with movement. At the same time, the fabric analogy has limits. Fabric is made of threads. Space-time, as far as we know, is not. It is continuous, not woven. Yet physicists wonder whether at the smaller scales space-time might have a structure, perhaps foamy or discrete, hinted at by attempts to unify quantum mechanics with relativity. If so, then the fabric we see at large scales could be an approximation, like a smooth cloth that looks continuous from a distance, but reveals individual fibers up close. For now, the true microscopic nature of space-time remains unknown, but the possibility that it is granular adds another layer to its dynamic character. The expansion of the universe provides another reminder of this dynamism. When astronomers discovered galaxies receding from each other, the natural interpretation was that space-time itself is stretching. It is not that galaxies are flying through space like projectiles from a common center. Rather, the distances between them increase because the metric of space changes. Every region of the universe participates in this expansion, even though gravitationally bound systems like solar systems or galaxies remain intact. This discovery transformed cosmology, and it showed that space-time evolves on the largest possible scales. Dark energy adds further complexity. The accelerated expansion observed today implies that space-time is not merely stretching, but stretching faster and faster. The simplest explanation is that space-time carries its own energy, and that energy drives expansion. If true, then space-time is not just geometry, but a reservoir of energy that can influence cosmic destiny. The dynamic fabric does more than respond to matter. It has an active role of its own. Another dramatic aspect is the way space-time behaves near black holes. As matter collapses under gravity, space-time curves more and more until it forms an event horizon, a region beyond which nothing, not even light, can escape. To an outside observer, time seems to slow as objects approach the horizon, while to the falling object, time proceeds normally until it reaches the singularity at the center. These extreme conditions highlight how intertwined space and time are, and how flexible the fabric can be under the weight of mass and energy. This same fabric connects directly to quantum fields. Every field exists within space-time, but space-time is not just a passive container. It can warp, stretch, and even fluctuate at small scales. The concept of space-time foam, introduced by John Wheeler, describes a picture in which at very tiny distances space-time itself might be turbulent, filled with quantum fluctuations. While this remains speculative, it suggests that the dynamism of space-time may extend down to the quantum realm, where geometry itself becomes uncertain. One of the puzzles in modern physics is how to reconcile this picture with quantum mechanics. General relativity describes space-time as smooth and continuous, while quantum theory demands that everything fluctuates and has uncertainty. Bringing these views together has proven challenging. Attempts like string theory and loop quantum gravity aim to describe space-time as emerging from more fundamental entities, perhaps strings vibrating in higher dimensions or networks of discrete loops. In these models, the familiar fabric is a large-scale approximation of something deeper. If these ideas are right, then calling space-time dynamic is an understatement. It is not just stretching and bending, but emerging from an even more restless foundation. Even without a full theory of quantum gravity, the evidence for spacetime's dynamism is overwhelming. Satellites confirm time runs differently depending on altitude and velocity, corrections that must be applied for GPS to function. Gravitational waves carry information from distant collisions, ringing spacetime like a vast cosmic drum. Observations of distant galaxies reveal the stretching of space itself, visible in the redshift of light. Every experiment, every measurement reinforces the idea that spacetime is not background but participant. This perspective changes how we think about beginnings. If spacetime is dynamic, then the question of where the universe came from cannot be separated from what spacetime itself is. The Big Bang is not an explosion in space, but an expansion of space. There was no pre-existing void waiting to be filled. Spacetime itself unfolded. To ask what came before is to step into territory where the concept of before may not even apply, because time is part of the fabric that was created. As we follow this thread, the questions multiply. Is spacetime infinite, or does it have boundaries? Is it continuous, or does it break into quanta at the smallest scales? Does it emerge from something even deeper, or is it fundamental? Each of these possibilities alters how we think about the cosmos, and each is tied to the recognition that spacetime is not fixed, but mutable. So when physicists say spacetime is a dynamic fabric, they are summarizing a century of discoveries. They are acknowledging that geometry itself has become part of physics, that the stage and the play are inseparable, that the flow of time and the shape of space are active participants in the story. The path forward is to explore how this fabric interacts with the quantum sea beneath it, how the fluctuations of fields and the curvature of space combine, and how this combination may explain not only the present universe but its origin. When Albert Einstein published his theory of general relativity in 1915, he gave the world a set of equations that reshaped how space, time, matter, and energy are understood. For him, the universe was not built upon a static backdrop. Instead, it was a system where geometry itself responded to the presence of matter and energy. Gravity became not a force acting across space, but a manifestation of space-time curvature. This framework has been tested and confirmed countless times, but in the early years it carried surprises even Einstein himself did not expect. One of the most striking was that his equations seemed to resist the idea of a static universe. At the beginning of the 20th century, most scientists assumed the cosmos was eternal and unchanging. Stars filled the sky, galaxies were not yet understood as distant systems, and the prevailing belief was that the universe simply existed in a steady state. Einstein shared that intuition, yet when he worked through the mathematics of general relativity, he discovered that the equations predicted either an expanding or contracting universe. A static solution was unstable, like balancing a pencil on its tip. To prevent that result, he added a term to his equations, the cosmological constant, which acted as a kind of repulsive force to counteract gravity and hold the universe in balance. It was an adjustment to force the math to match his expectations. Not long after, however, evidence began to mount that the universe might not be static at all. Astronomers such as Vesto Slipher had measured the spectra of distant nebulae, finding that many appeared to be moving away from Earth. Their light was redshifted, shifted toward longer wavelengths, suggesting recession. At the time, the nature of those nebulae was debated. Were they small clouds inside our own galaxy, or vast systems in their own right? The question was answered decisively in the 1920s when Edwin Hubble used the Mount Wilson Observatory to measure distances to these nebulae. By identifying variable stars known as Cepheids, which act as standard candles, he determined that the Andromeda Nebula and others were far outside the Milky Way. They were separate galaxies, and they were receding. When Hubble compared the distances of many galaxies with their redshifts, he found a clear relationship. The farther a galaxy was, the faster it seemed to move away. This was the first observational evidence that the universe is expanding. Suddenly, Einstein's equations did not need the cosmological constant to balance them. The natural solutions, which described expansion, matched the data. Einstein reportedly called his introduction of the constant his greatest blunder, though modern physics has revived the idea in a different context with dark energy. The discovery of expansion was revolutionary. It meant the universe was not eternal and static, but dynamic and evolving. It implied that in the past, galaxies were closer together, the cosmos denser and hotter. Run the expansion backward, and one arrives at an origin, a time when the universe was compressed into an extremely small, hot state. This was the seed of what later became the Big Bang model. Einstein at first was skeptical of such an origin. He resisted the idea of a beginning to time itself, preferring a universe without singularities. But others pursued the implications. Alexander Friedmann, a Russian mathematician, derived solutions to Einstein's equations that described expanding universes without needing a cosmological constant. His work showed that relativity naturally allowed for a dynamic cosmos. Later, Belgian physicist and priest Georges Lemaitre extended these ideas, suggesting that the universe had begun from a primeval atom, a dense state that exploded and expanded. Though controversial at first, his proposal aligned with Hubble's observations. Over time, more evidence accumulated. The distribution of galaxies, the relative abundance of light elements such as hydrogen and helium, and later, the discovery of the cosmic microwave background all pointed toward an expanding universe with a hot, dense origin. Einstein's equations, which once seemed to demand a static universe, had in fact opened the door to a dynamic picture in which the cosmos itself has a history. This interplay between theory and observation illustrates how science evolves. Einstein's equations suggested possibilities he did not initially embrace. Observations challenged long-held assumptions. Gradually, the two converged into a coherent picture. The universe is not fixed. It grows, stretches, and evolves. Relativity gave the framework, and astronomy provided the evidence. Together, they overturned the idea of eternal stasis. The expansion is not like an explosion sending matter into empty space. Instead, space itself expands. Every region stretches, carrying galaxies apart. The analogy of raisins in rising dough is often used. As the dough rises, the raisins move away from each other, not because they are travelling through the dough, but because the dough itself is expanding. In the same way, galaxies recede not because they are flying through space, but because space-time itself stretches between them. This understanding connects directly back to the concept of space-time as a fabric. Expansion is a change in the geometry of that fabric. Relativity provides the mathematics to describe how distances evolve, how light is redshifted as it travels, and how the history of the cosmos can be reconstructed. The universe is not a collection of objects moving through emptiness, but a single structure unfolding. Einstein's role in this transformation is complex. His equations predicted the possibility. His initial reluctance slowed acceptance. But once the evidence was clear, relativity became the foundation of modern cosmology. Even today, the models of the universe we use are based on solutions to Einstein's field equations, refined by new discoveries but rooted in the same principles. What makes this story remarkable is how it connects scales. The curvature of space-time, described by equations on paper, determines the motion of galaxies separated by millions of light-years. The physics of geometry guides the destiny of the cosmos. From the bending of light near the sun to the stretching of space across billions of parsecs, relativity links the local with the cosmic. And still, questions remain. If the universe is expanding, what drives that expansion? Is it purely the initial conditions of the Big Bang, or does something like dark energy continue to push it outward? If the expansion can accelerate, as observations suggest, what role does the cosmological constant play after all? Did Einstein's so-called blunder anticipate a deeper truth? At the beginning of the 20th century, the night sky looked familiar, but the scale of the cosmos was still misunderstood. Astronomers knew of the Milky Way, of stars filling its spiral arms, and of patches of light known as nebulae. But what those nebulae were remained uncertain. Some believed they were small clouds of gas within our own galaxy. Others argued they might be entire star systems far beyond. The answer to this question would transform astronomy and reshape our understanding of the universe. It was in this context that Edwin Hubble began his work, building on tools, ideas, and observations that were just reaching maturity. Hubble was a meticulous observer who used the Hooker telescope at Mount Wilson Observatory in California, then the largest in the world. With its 100-inch mirror, it gave astronomers unprecedented clarity and reach. He set his sights on the great nebulae scattered across the sky, trying to settle the debate over their true nature. Were they local clouds of dust and gas or distant galaxies in their own right? The tool he used to answer this question was a special kind of star called a Cepheid variable. Cepheids have a remarkable property. Their brightness varies in a predictable cycle, and the length of that cycle is directly related to their intrinsic luminosity. The longer the period of variation, the brighter the star actually is. By measuring the period, astronomers can determine how luminous the star should be, and by comparing that to how bright it appears from Earth, they can calculate its distance. This makes Cepheids cosmic yardsticks, allowing distances to be measured far beyond what parallax or other methods can provide. Hubble identified Cepheid variables in the Andromeda Nebula, carefully measuring their periods and brightness. When he worked out their distances, the numbers were astonishing. The stars were far too distant to be part of the Milky Way. Andromeda was not a cloud within our galaxy, but a separate system altogether, another galaxy comparable in size to our own. This discovery resolved the great debate between those who thought the Milky Way encompassed the entire universe and those who suspected it was just one island among many. Hubble had shown decisively that the cosmos extended far beyond our galaxy, but his work did not stop there. As he studied more galaxies and compared their spectra, he noticed something striking. Many galaxies showed red-shifted spectral lines, meaning their light was shifted toward longer wavelengths. The redshift could be interpreted as a sign that the galaxies were moving away from us. At first glance, it seemed as though the Milky Way might be at the center of an outward rush, with galaxies flying in all directions. But as Hubble collected more data, a deeper pattern emerged. The pattern was that the farther away a galaxy was, the greater its redshift. In other words, the more distant the galaxy, the faster it appeared to be receding. This linear relationship between distance and velocity became known as Hubble's law. It was the first clear observational evidence that the universe is expanding. Space itself was stretching, and galaxies were carried along with it. This result was revolutionary because it confirmed theoretical predictions already hinted at by general relativity. Solutions to Einstein's equations had suggested that the universe could not be static. Either it must expand or contract. Hubble's discovery provided the observational confirmation, turning a mathematical possibility into a physical reality. The implications were profound. If the universe is expanding now, it must have been smaller and denser in the past. Extrapolated backward, this led to the idea of a beginning, a time when everything was compressed into an extremely hot, dense state. Although Hubble himself avoided speculating too much about the origin, his observations laid the foundation for the Big Bang model. It is important to note how careful Hubble was. He was not quick to claim that his discovery proved the universe was expanding. He presented the data with caution, letting others draw conclusions. But the relationship he uncovered was too consistent to ignore. Astronomers around the world began to accept that the cosmos was not eternal and unchanging, but dynamic and evolving. One of the reasons this discovery was so significant is that it transformed the scale of human understanding. For millennia, people had believed the universe was confined to what they could see with their eyes. Even after telescopes revealed more stars, the idea that the Milky Way contained everything persisted. Hubble shattered that picture. The universe was not just larger than expected, it was vastly larger, filled with countless galaxies, each containing billions of stars. And beyond size, it was dynamic, with every system moving away as space itself expanded. Hubble's work also set the stage for a new kind of cosmology. No longer could astronomers focus only on cataloguing stars or charting local structures. They now had to consider the universe as a whole, asking questions about its history, its fate, and the laws governing its expansion. The observational evidence of recession velocities gave rise to models of cosmic evolution, eventually leading to the hot Big Bang scenario, cosmic microwave background predictions, and inflationary theories. There is a human element to this story as well. Hubble was trained in both astronomy and law, and his career path was not straightforward. Yet he combined patience, precision, and ambition in a way that changed science forever. His work at Mount Wilson required long nights of observing careful photographic plates and meticulous measurements. He built on the contributions of Henrietta Leavitt, who discovered the Cepheid period luminosity relation, and of Vesto Slipher, who measured galaxy redshifts. Science is rarely the product of one individual, and Hubble's discovery was no exception. But his synthesis of distance and velocity was the breakthrough moment that tied it all together. Today, the legacy of his discovery lives on not only in the Hubble constant, which describes the rate of cosmic expansion, but also in the Hubble Space Telescope, which has extended his vision far beyond what he could have imagined. Images from that telescope have revealed galaxies billions of light years away, showing the universe as it was when it was young. Each of those images is a direct descendant of the insight Hubble provided, the recognition that the cosmos is expanding and that distance is tied to recession velocity. The story continues to evolve. Measurements of the Hubble constant using different methods have produced slightly different results, leading to what is now known as the Hubble tension. Whether this discrepancy signals new physics or simply unresolved measurement issues remains to be seen. But the very fact that cosmologists debate it shows how central Hubble's discovery remains. His work continues to shape the frontier of research a century later. In the larger picture, Hubble's discovery also changes how we think about our place in the universe. The Milky Way is not the centre of expansion. Every galaxy sees others receding, because expansion occurs everywhere. There is no preferred vantage point. The cosmos looks the same in every direction, at least on large scales, and the laws of physics apply uniformly. This cosmological principle, supported by Hubble's work, underlies modern cosmology. When we look up now and see galaxies drifting apart, we are watching the legacy of Hubble's insight unfold in real time. His discovery turned the night sky from a static backdrop into a living history, a record of expansion written in starlight. Every red-shifted spectrum, every faint smudge of a distant galaxy is part of that story. When most people hear the phrase Big Bang, they imagine an explosion, a sudden burst of energy from a point in space, sending matter flying outward into emptiness. The name itself encourages that picture, and it has been reinforced countless times in books, shows, and casual conversations. But the reality, as physicists understand it, is different. The Big Bang was not an explosion in space, it was the rapid expansion of space itself. That distinction matters because it changes how we think about what the universe was, what it became, and what questions remain. The starting point is to recognize what the observations demand. When Edwin Hubble measured the redshifts of galaxies, he found that more distant galaxies recede faster. This pointed to an expanding universe. If space is stretching today, then in the past it must have been smaller. Wind the clock backward, and galaxies converge. Distances shrink. The universe grows hotter and denser as matter and radiation are compressed into a smaller volume. Extrapolated far enough, this leads to a state where densities were enormous and temperatures extreme. That is what scientists mean when they talk about the Big Bang. Not a fireball in space, but the evolution of the cosmos from a very hot, dense initial state. Evidence for this picture comes from multiple sources. One is the abundance of light elements. In the early universe, when temperatures were high enough, nuclear reactions occurred in a process called Big Bang nucleosynthesis. Hydrogen fused into helium, with traces of deuterium and lithium also produced. The predicted ratios from these reactions match what astronomers observe in the oldest stars and interstellar clouds. This agreement tells us that the universe really did pass through a phase when it was hot and dense enough for nuclear reactions to occur everywhere. Another piece of evidence is the cosmic microwave background radiation. In the early stages, the universe was filled with a plasma of particles and photons so hot and dense that light could not travel freely. Photons scattered constantly off electrons, trapping radiation. As the universe expanded and cooled, it reached a point where electrons could combine with protons to form neutral atoms. This process, called recombination, freed the photons, allowing them to stream through space largely unhindered. Those photons have been travelling ever since, stretched by the expansion of space into the microwave region of the spectrum. Today, they form a nearly uniform glow across the entire sky. Detected first in 1965 by Arno Penzias and Robert Wilson, the cosmic microwave background is one of the strongest confirmations of the hot Big Bang model. This radiation is not perfectly smooth. Small variations in its temperature measured in millionths of a degree reveal the seeds of structure. They are the imprints of density fluctuations in the early universe, slight differences in matter distribution that later grew into galaxies and clusters. These variations tell us about the conditions only a few 100,000 years after the Big Bang, making the cosmic microwave background a window into the young cosmos. So when we talk about the Big Bang, we're talking about a set of conditions, an early universe that was small, dense, and hot, nuclear reactions that forged light elements, photons that decoupled from matter and became the background radiation we still see, and fluctuations that seeded cosmic structure. It is not a moment of creation in the sense of something from nothing. It is the beginning of the expansion as we can trace it, the earliest state accessible with current physics. This raises the question of what the Big Bang does not describe. It does not explain why the universe exists. It does not describe a singularity in which everything is compressed into a point, though simple extrapolations of relativity suggest such a state. At those densities and energies, our current theories break down. Quantum effects must matter, but a full theory of quantum gravity does not yet exist. So the singularity is a sign that the mathematics has reached its limit, not a literal description of reality. Instead, the Big Bang describes the evolution of the universe from a fraction of a second after whatever earlier state existed. It tells us how matter and radiation behaved, how expansion proceeded, how elements formed, and how light was released. It is a theory of history, not of ultimate origins. That distinction is important because it keeps the boundaries of knowledge clear. Still, the theory has grown richer over time. Originally, the Big Bang model faced challenges. Why is the universe so uniform on large scales if distant regions could not have communicated with each other? Why is space so nearly flat, with geometry balanced between open and closed? Why are there no magnetic monopoles, hypothetical particles predicted by some theories? These puzzles led to the idea of cosmic inflation, a brief period of accelerated expansion in the early universe. Inflation can smooth out irregularities, flatten space, and dilute unwanted relics. It also provides a mechanism for generating the initial fluctuations that grew into galaxies, linking quantum processes with cosmic structure. Observations of the cosmic microwave background have supported inflation by showing the right spectrum of fluctuations, consistent with what inflation predicts. While details remain debated, the broad picture fits remarkably well. The Big Bang, enriched by inflation, is now the standard model of cosmology. It is also worth noting what the Big Bang is not. It is not an explosion with a centre. Every point in the universe sees other points receding, because space itself expands everywhere. There is no edge from which expansion began, no outside into which the universe is growing. The universe is all there is, and expansion is the stretching of its own fabric. This can be difficult to picture, but analogies help. One is the surface of a balloon. As it inflates, every point on the surface moves away from every other. There is no privileged centre on the surface itself. Likewise, in three-dimensional space, every galaxy sees others receding, and there is no single point from which they all fly. The Big Bang also does not imply a sudden burst into pre-existing emptiness. Space and time themselves are part of the expansion. Asking what the universe expanded into may not even make sense, because there is no outside space in which it sits. Expansion is the growth of distances within the universe itself. This understanding shifts the focus from an event to a process. The Big Bang is the name we give to the process by which the universe evolved from a dense, hot state into the expanding cosmos we see. It is an ongoing unfolding, not a single explosion. Every photon of background radiation, every ratio of helium to hydrogen, every cluster of galaxies is part of that process. As observations improve, the details of this story become clearer. Satellites such as COBE, WMAP and Planck have mapped the microwave background with increasing precision, confirming predictions of the hot Big Bang and refining measurements of cosmological parameters. These include the age of the universe, about 13.8 billion years, and the proportions of ordinary matter, dark matter and dark energy. Each result ties back to the framework of the Big Bang, showing that the theory is not just a broad sketch but a quantitative description. At the same time, mysteries remain. Dark matter, which outweighs ordinary matter by a factor of about 5, is not part of the original Big Bang picture, but is required to explain galaxy rotation and structure formation. Dark energy, responsible for accelerated expansion, is another ingredient. Both are consistent with the framework but extend it, reminding us that even with a successful model, much remains unknown. What the Big Bang really describes, then, is a history with clear milestones. The first fractions of a second when inflation may have occurred, the first 3 minutes when nucleosynthesis produced light elements, the first 380,000 years when atoms formed and photons decoupled, leaving the microwave background, the billions of years that followed as gravity amplified fluctuations into galaxies, stars and planets. Each stage is supported by evidence. Each connects the past to the present. The importance of this picture cannot be overstated. It tells us that the universe has a finite age, that it has changed dramatically over time, and that its present structure arose from tiny fluctuations in the earlier state. It connects the larger scales of cosmic evolution to the smaller scales of quantum fluctuations. It provides a framework within which questions of origin, destiny, and structure can be asked with rigor. And yet, the Big Bang is not the end of inquiry. It leaves open the question of what came before, if that phrase even has meaning. It leaves open the question of why the laws of physics take the form they do, why the vacuum has the energy it has, and why the universe exists at all. These questions are not answered by the Big Bang, but are illuminated by it, because they define the boundaries where knowledge ends and curiosity begins. By the time the Big Bang model was accepted as the best explanation for the expanding universe, a series of puzzles began to trouble physicists. The model described a hot, dense beginning and explained the formation of light elements and the cosmic microwave background. It matched observations remarkably well. And yet there were aspects of the cosmos that seemed difficult to account for within the simple picture of expansion alone. Why is the universe so uniform on large scales, when distant regions could not have communicated with one another? Why is space so nearly flat, with no obvious reason for such fine balance? Why are relics predicted by some theories, like magnetic monopoles, not observed? These questions pointed to something missing in the story. The solution that emerged, called inflation, changed the way scientists think about the earliest instance of the universe. The problem of uniformity is one of the clearest. When we look at the cosmic microwave background, we see that its temperature is nearly the same in every direction. The variations are tiny, only a few parts in 100,000. But according to the simplest Big Bang picture, regions of the sky separated by vast distances should never have been in causal contact. Light, or any signal, would not have had enough time to travel between them. So how could they have reached such similar conditions? This is called the horizon problem. Another issue is flatness. Measurements show that the geometry of the universe is very close to flat, meaning parallel lines remain parallel, and the density is almost exactly at the critical value. Yet in the Big Bang model without modification, any departure from flatness would grow over time. For the universe to be as flat as it is today, it must have been extraordinarily fine-tuned in the beginning, balanced to many decimal places. This is called the flatness problem. A third puzzle involves relics predicted by grand unified theories, such as magnetic monopoles. These are hypothetical particles with a single magnetic pole, north without south, or vice versa. Some theories suggest they should have been produced in great abundance in the early universe, yet no evidence for them has been found. If the Big Bang began from a hot dense state without modification, monopoles should be common. Their absence is the relic problem. In the late 1970s and early 1980s, physicists proposed a new idea to address these puzzles. The key was to imagine that in the very first fraction of a second, the universe underwent a period of exponential expansion, growing at an extraordinary rate. This expansion, called inflation, would stretch space by a huge factor in an incredibly short time. Instead of doubling or tripling in size, the universe could expand by a factor of 1026 or more in less than a trillionth of a second. How does this solve the puzzles? For the horizon problem, inflation allows distant regions of the universe to have once been close together. Before inflation, the universe was small enough for all regions to interact and reach similar temperatures and densities. Then inflation stretched that small uniform patch to cosmic scales, so that when we look across the sky, we see regions that appear disconnected but were once in contact. The uniformity is no longer mysterious. For the flatness problem, inflation drives the universe toward flatness. Just as the surface of an inflating balloon appears flatter as it grows, inflation smooths out any initial curvature. After such rapid growth, the observable universe would look nearly flat no matter what its initial geometry was. This explains why measurements today show such precise flatness without requiring fine-tuned initial conditions. For the relic problem, inflation provides a dilution mechanism. Any exotic particles produced before inflation would be stretched and diluted to such low densities that they would be essentially unobservable. Monopoles, if they exist, would be spread so thin that they would be exceedingly rare, explaining why none have been detected. Beyond solving these puzzles, inflation also provides a mechanism for the origin of cosmic structure. Quantum fluctuations in the early universe, normally microscopic, would be stretched by inflation to cosmic scales. These fluctuations would then act as seeds for the formation of galaxies and clusters. The tiny variations seen in the cosmic microwave background match the statistical properties predicted by inflation, providing strong support for the idea. The driving force behind inflation is thought to be a scalar field, often called the inflaton. This field would have a potential energy that remains nearly constant for a period, causing space to expand exponentially. Eventually, the field would decay, releasing its energy into particles and radiation, reheating the universe and beginning the hot Big Bang phase. While the exact nature of the inflaton is unknown, the general mechanism is flexible and fits well with observations. The proposal of inflation was bold, but it has been tested in many ways. Measurements of the cosmic microwave background by satellites such as WMAP and Planck have shown the spectrum of fluctuations is nearly scale invariant, meaning variations look similar across different scales. This matches the predictions of inflation. The slight deviations from exact scale invariance also align with models of how inflation might end. Polarization patterns in the microwave background are also being studied for signs of primordial gravitational waves, another possible signature of inflation. While these have not yet been definitively observed, the search continues, because such a detection would provide direct evidence of inflation stretching of space-time. It is worth noting that inflation is not a single theory but a family of models. Different shapes of the inflaton potential lead to different details. Some models predict eternal inflation, in which inflation never ends everywhere, but continues in some regions, creating a multiverse of bubble universes. Others predict a graceful exit, with inflation ending uniformly across space. Each variation has different implications, but all share the basic feature of rapid expansion. Critics sometimes point out that inflation introduces new assumptions, such as the existence of the inflaton field, which has not been directly observed. They argue that alternative models might explain the same observations. Still, inflation remains the leading explanation, because it so elegantly solves multiple problems and makes predictions that match data. Whether it is the final answer or a step towards something deeper is an open question. The idea that the entire universe was once smaller than a subatomic particle, and then expanded to cosmic scales in less than a heartbeat is difficult to picture, but the mathematics supports it. The consequences match what we see. The smoothness of the microwave background, the flatness of space, the absence of relics, the spectrum of fluctuations, all of these align with inflation's predictions. And so inflation has become part of the standard cosmological model, not replacing the Big Bang but extending it. The Big Bang describes the hot, dense evolution after inflation, while inflation sets the initial conditions. Together they provide a coherent story from the earliest instance to the present cosmos. This story also points forward, because inflation suggests that the structure of the universe we see today may be just one realization among many possibilities. If inflation can continue eternally in some regions, then there may be countless other universes, each with different properties, born from the same mechanism. While this idea remains speculative, it shows how inflation opens the door to new ways of thinking about reality. What began as a solution to technical puzzles has grown into a profound framework connecting quantum mechanics, field theory, and cosmology. Inflation bridges the smallest and the largest, turning quantum fluctuations into galaxies and linking the behavior of fields to the expansion of the universe itself. It is a reminder that in physics, the answers to practical problems often reveal deeper truths about existence. When you look up at the night sky, every star, every cluster, every faint streak of light from a distant galaxy has a story that stretches back to the earliest moments of the universe. These immense structures of gas, dust, and stars seem impossibly vast compared to the microscopic world of quantum mechanics. Yet modern cosmology has revealed a profound connection between the two. The seeds of galaxies and stars, the very beginnings of cosmic structure, were planted in quantum fluctuations that occurred during the earliest instance after inflation. What began as tiny variations at subatomic scales grew over billions of years into the luminous structures we now see scattered across the cosmos. To understand this, start with inflation. During that incredibly brief phase, space expanded exponentially, stretching everything within it by an unimaginable factor. Quantum fields cannot remain perfectly smooth. They fluctuate because of the uncertainty principle. In ordinary conditions, those fluctuations remain microscopic, far too small to notice. But during inflation, they were stretched along with space itself. What was once smaller than a proton could be stretched to astronomical scales. When inflation ended, these imprinted irregularities were left behind in the distribution of matter and energy. These irregularities were tiny, on the order of 1 part in 100,000, yet they were enough. As the universe continued to expand and cool, regions that were slightly denser attracted more matter through gravity. Over millions of years, these small differences grew. Matter clumped together, forming filaments and knots in the cosmic web. Eventually, gas clouds collapsed into galaxies, stars ignited, and the universe became structured. Evidence for this process is written into the cosmic microwave background. When satellites like COBE, DARMAP, and Planck mapped its faint temperature variations, they revealed patterns that match precisely what inflation predicts. The fluctuations are random, but follow a specific statistical distribution, one that arises naturally from quantum processes. This means the very patterns we see across the sky are snapshots of quantum fluctuations frozen into place nearly 14 billion years ago. Every galaxy, every cluster, every star can trace its origin to these seeds. The transition from quantum noise to cosmic structure is one of the most remarkable bridges in science. On one side are the rules of quantum mechanics, describing probabilities and uncertainties at the smallest scales. On the other side is the universe of galaxies stretching across billions of light years. Inflation acts as the bridge, magnifying microscopic fluctuations into macroscopic inhomogeneities. Gravity then amplifies those inhomogeneities into the rich structures we observe. Consider what this means. The position of galaxies, the clustering of clusters, the arrangement of the cosmic web all reflect patterns laid down by random quantum fluctuations. In a sense, the universe's large-scale architecture is a fossil record of the uncertainty principle. This is not poetic language, but a literal statement of physics. Without quantum fluctuations, there would be no galaxies, no stars, and no planets. The universe would be smooth, filled with uniform radiation, and matter, with nothing to break the symmetry. Structure exists because randomness at the quantum level provided the seeds. As matter began to accumulate around these seeds, its evolution was guided by both gravity and pressure. In the early universe, before recombination, matter and radiation were tightly coupled. Photons scattered off electrons, preventing gas from collapsing freely. This created acoustic oscillations, sound waves in the plasma of the early cosmos. These oscillations left imprints in the cosmic microwave background, and later in the distribution of galaxies, known as baryon acoustic oscillations. The peaks and troughs of these oscillations reflect the same initial fluctuations stretched by inflation. When the universe cooled enough for neutral atoms to form, photons decoupled and matter could collapse more freely under gravity. Denser regions grew denser, while underdense regions became emptier. Dark matter played a crucial role here. Unlike ordinary matter, it did not interact with radiation, so it could start clustering earlier. Its gravitational influence created wells into which gas could fall, accelerating the growth of galaxies. The seeds planted by quantum fluctuations thus sprouted first in dark matter, which then guided the visible structures of stars and galaxies. Over hundreds of millions of years, these growing clumps of matter became the first halos of dark matter and gas. Within them, gravity pulled gas together until it was dense enough to ignite nuclear fusion. The first stars, massive and short-lived, lit up the cosmos. They produced heavy elements, exploded as supernovae, and seeded their surroundings with the materials needed for later generations of stars and eventually planets. Galaxies formed as collections of these stars, bound together by gravity, tracing the patterns laid down in the earliest instance. Even today, simulations of cosmic structure formation begin with maps of initial fluctuations consistent with inflation. When physicists run those simulations forward under the influence of gravity and cosmic expansion, the results resemble the observed universe. Filaments of galaxies, vast voids, clusters and superclusters emerge, all in agreement with surveys of the sky. This is strong evidence that the seeds were indeed quantum in origin. The scale of this process is staggering. A fluctuation in a quantum field, perhaps in the inflaton or related fields, might begin at scales smaller than an atomic nucleus. Inflation stretches it until it spans light years. Gravity takes hold, pulling matter into the denser regions. Over billions of years, entire galaxies containing hundreds of billions of stars form in those regions. And within those galaxies, stars produce planets, and on at least one of those planets, life emerges to wonder about its origins. All of this rests on the reality that the quantum vacuum is not empty, and that its fluctuations left an indelible mark on the cosmos. This connection also highlights the unity of physics. It shows that the same rules governing electrons in atoms also shape the universe at its larger scales. Quantum mechanics is not confined to laboratories. Its fingerprints cover the sky. The discovery that fluctuations in a microscopic field determined the placement of galaxies is a profound reminder that the smallest and largest are inseparable. Observational cosmology continues to refine this picture. The statistical properties of the microwave background fluctuations, their correlations across different scales, and their polarization all provide tests of inflationary models. The fact that the data matches the predictions gives confidence that this story is correct. The search for gravitational waves from inflation, imprinted as a specific pattern in the polarization of the microwave background, remains ongoing. If detected, it would provide direct evidence of the stretching of quantum fluctuations into cosmic seeds. The path from quantum fluctuations to galaxies also raises new questions. Why were the fluctuations distributed as they were? Why did the inflaton field have the properties that allowed this? Could different fluctuations in other regions of an eternally inflating cosmos produce entirely different structures, perhaps universes with different physical laws? These questions show that the seeds we observe may be part of a much larger landscape of possibilities. But even without those speculative extensions, the core idea remains clear. The structure of the universe is the amplified echo of quantum uncertainty. The patterns of galaxies are not arbitrary. They are the inevitable outcome of small fluctuations stretched and grown by inflation and gravity. Every time we map the cosmic web, we are tracing those echoes. Every time we look at the microwave background, we are looking at the seeds themselves. This perspective changes how we see the night sky. A galaxy is not just a collection of stars. It is a manifestation of randomness frozen into structure. A star is not just a ball of fusion. It is part of a lineage that began with a fluctuation in the earliest moments. Even our own solar system, with its planets and life, can trace its ancestry back to quantum seeds. And the story continues forward. The seeds planted in the early universe not only gave rise to structure, but also determined the fate of that structure. As expansion continues, galaxies move apart, clusters drift away, and the cosmic web stretches. The seeds determine not only the past, but also the future arrangement of the universe. They are the blueprint on which the entire history of structure is written. After tracing the seeds from quantum fluctuations to galaxies and stars, the natural question becomes how such a universe balances its books, and whether the total energy of everything might truly add up to zero. When people first hear the idea that the universe might have come from nothing, the natural reaction is to think it violates the most basic rules of physics. After all, nothing should produce nothing. Energy should be conserved. You cannot get something for free. But when physicists talk about a universe from nothing, they mean something subtler, rooted in the deep structure of conservation laws. The remarkable fact is that, under the right conditions, a universe can arise without breaking those laws at all. To understand this, it helps to recall what conservation means in physics. The principle of conservation of energy says that energy cannot be created or destroyed, only transformed. The principle of conservation of momentum says that momentum cannot appear or vanish, only be transferred. These rules are not arbitrary, they are tied to the symmetries of nature. A powerful insight from Emmy Noether in 1915 showed that every conservation law corresponds to a symmetry. If the laws of physics do not change in time, energy is conserved. If the laws of physics do not change in space, momentum is conserved. These links are not coincidences but deep truths about how the universe works. In everyday life, conservation laws are reliable guides. A ball rolling down a hill loses potential energy but gains kinetic energy, with the total staying the same. A pendulum swings, trading height for speed, but the sum remains constant if friction is ignored. These are familiar examples, and they confirm our intuition that you cannot get something for nothing. But the universe as a whole operates under conditions where gravity plays a dominant role, and gravity has unusual properties that make the story more interesting. The key is that gravity carries negative energy. It may sound strange, but in physics, the potential energy of a gravitational system is defined to be negative relative to zero at infinite separation. When two masses attract, their potential energy decreases, becoming more negative as they draw closer. At the same time, kinetic energy increases as they accelerate. The balance between positive kinetic energy and negative potential energy is what allows orbital systems to remain stable. The Earth and the Moon, for example, form a system where the total energy is negative, bound together by gravity. Now imagine applying this principle to the entire universe. The matter and radiation it contains carry positive energy, but the gravitational field that binds them carries negative energy. If the amounts are exactly balanced, the total energy of the universe could be zero. This is the essence of the zero-energy universe hypothesis. In such a picture, the universe does not violate conservation laws by existing. It balances its books perfectly, with positive and negative contributions cancelling out. Something can arise without requiring net energy, because the total is still zero. This idea was first seriously proposed in the 1970s and 1980s, as cosmologists began connecting quantum field theory with relativity. Alan Guth, who developed the theory of inflation, pointed out that inflation could create enormous amounts of matter and radiation, but the negative energy of gravity could balance it. As space expands, more matter and radiation can appear, but the gravitational energy grows more negative, keeping the total unchanged. The universe expands, structures form, and yet conservation laws remain satisfied. The concept also fits naturally with quantum mechanics. In quantum field theory, fluctuations can produce particle-antiparticle pairs from the vacuum, provided they annihilate quickly enough that energy conservation is not violated. This is permitted by the uncertainty principle, which allows brief borrowings of energy within strict limits of time. If the entire universe is a fluctuation, then its persistence requires a mechanism to balance energy. The interplay of positive matter energy and negative gravitational energy provides exactly that. There is a useful analogy in particle physics. When a particle and its antiparticle annihilate, they produce photons, preserving energy. When photons fluctuate into a particle-antiparticle pair, the process is also consistent with conservation, provided the accounting is correct. In the same way, the universe can be seen as a large-scale fluctuation that respects conservation, even if at first glance it looks like something emerging from nothing. This picture does not answer every question, of course. It does not explain why the laws of physics allow such balancing acts in the first place, or why the symmetries that guarantee conservation exist. But it shows that conservation laws are not barriers to a universe from nothing. On the contrary, they make such a universe possible. An important detail is that defining energy in general relativity is not as straightforward as in Newtonian physics. Energy can be localized for matter and radiation, but gravitational energy is more elusive. In curved space-time, energy is not always conserved in the same simple sense as in flat space. However, in cosmology, when the entire universe is considered, the zero-energy concept remains a consistent way to think about the balance between matter and gravity. This balance is supported indirectly by observations. The density of matter, radiation, and dark energy, when combined with measurements of the geometry of the universe, show that the total density is very close to the critical value needed for flatness. A flat universe is exactly what inflation predicts, and it is consistent with a zero-energy balance. If the universe had significant positive or negative total energy, its geometry would deviate strongly from flatness. The fact that it does not is evidence, though not proof, that the balance may indeed be exact. The role of dark energy complicates the picture, since its nature is not fully understood. It appears as a form of vacuum energy, uniform across space, and its contribution to the energy budget is large. But even with dark energy included, the idea of balance remains possible. The mathematics allows the vacuum itself to contribute energy, while gravity offsets it. The details are subtle, but the principle that the total can sum to zero remains. It is also worth reflecting on how unusual this is compared to human intuition. In daily life, everything has a cost. Building requires energy, motion requires fuel. Nothing appears spontaneously. But the universe is not bound by the same rules we experience on Earth. It operates on principles of symmetry and balance that allow structures to exist without violating conservation. When physicists say the universe could come from nothing, they are not ignoring conservation, they are invoking it. The very laws that seem to forbid creation without cause turn out to permit it under the extraordinary conditions of cosmology. The story also highlights the unifying power of Noether's theorem. The symmetries of time and space guarantee conservation laws. If those symmetries hold in the universe as a whole, then conservation is built into the fabric of reality. That conservation can allow a zero-energy balance is one of the most striking consequences of this deep connection between symmetry and physics. Of course, questions remain open. Does the total energy really sum to zero exactly, or only approximately? If it is exact, is this a necessity or a coincidence? If approximate, what sets the small imbalance? These are not trivial questions, and answering them may require a full theory of quantum gravity. Yet the broad principle, that conservation does not forbid a universe from nothing but makes it possible, stands as one of the key insights of modern cosmology. This way of looking at the universe also changes how we think about its fate. If the balance of positive and negative energy has held since the beginning, it may continue indefinitely. If dark energy dominates, expansion will accelerate forever, with gravity unable to halt it. If balance shifts, different futures are possible. In every scenario, conservation continues to guide the evolution, ensuring that the total remains consistent. This perspective helps frame the larger question of why there is something rather than nothing. Physics may not answer the ultimate why, but it shows that nothing in the physical sense does not mean emptiness. It means a vacuum state with fluctuations, a balance of energies, and symmetries that allow existence without breaking rules. Nothing, in this sense, already contains the potential for something. Seen this way, the conservation laws are not obstacles but invitations. They show how a universe can exist naturally, consistent with the deepest principles of physics. They tie the grandest structures to the simplest symmetries. They reveal that something from nothing is not a contradiction, but a consequence of the balance written into the fabric of space-time. When physicists speak of the possibility that the total energy of the universe might be exactly zero, they are pointing toward one of the most surprising and subtle ideas in modern cosmology. The claim is not that there is no matter, no light, and no motion. Quite the opposite. The universe is filled with stars, galaxies, radiation, and particles of every kind. It is full of energy in all its familiar forms. But the zero-energy universe hypothesis says that when you add up all of these positive contributions and balance them against the negative contribution of gravity, the result could be precisely nothing. The universe as a whole may have emerged not by breaking conservation laws, but by satisfying them in the most elegant way possible. by always adding to zero. To understand this idea, it helps to recall how energy is defined in gravitational systems. In Newtonian mechanics, the potential energy of two masses is set to zero when they are infinitely separated. As they come closer together, their potential energy decreases, becoming more negative. At the same time, their kinetic energy increases as they accelerate under mutual attraction. The total energy of the system is the sum of kinetic and potential. For bound systems like planets orbiting stars, the total is negative, meaning the system does not have enough energy for the bodies to escape one another. This concept of negative gravitational energy extends naturally to cosmology. The universe is filled with matter and radiation carrying positive energy. But the gravitational field that holds it all together contributes negative energy. If the magnitudes of the two contributions are exactly equal, the sum is zero. That balance could explain how the universe came into being without requiring net energy input. Instead of asking where the universe found its energy, we might say it never needed to find any at all. This hypothesis gained traction in the 1970s and 1980s as physicists explored the consequences of inflation and quantum field theory. Alan Guth, who first proposed inflation, emphasized that while inflation generates enormous amounts of matter and radiation, it also generates an equal and opposite amount of gravitational energy. The growth of space allows both to increase, but always in balance. Matter and radiation fill the cosmos, gravity grows more negative, and the total remains zero. The universe expands but never tips the ledger. One way to picture this is to imagine borrowing money while simultaneously taking on an equal amount of debt. Your assets and liabilities may grow, but your net worth stays the same. In cosmology, positive energy is like the assets, negative gravitational energy is like the debt, and the net result is always zero. The analogy is imperfect but captures the sense of balance. The universe may be vast and full, but it could still have a total energy of nothing. Evidence for this possibility comes indirectly from measurements of the universe's geometry. Observations of the cosmic microwave background, galaxy distributions, and distant supernovae all suggest that the universe is spatially flat to within a small margin of error. Flatness corresponds to the critical density of energy, the exact amount needed for expansion to balance gravity. A flat universe is consistent with the total energy summing to zero. Inflation provides a natural explanation for why flatness should be so precise, stretching any curvature to near invisibility. Together, inflation and flatness support the idea of balance. The concept also resonates with quantum mechanics. In quantum field theory, particles can emerge temporarily from the vacuum as long as they annihilate quickly, preserving conservation. If the universe is viewed as a large-scale fluctuation, then its persistence requires a mechanism to conserve energy. The zero energy balance provides exactly that mechanism. The universe may be vast, but in total it does not cost anything to exist. This is not merely philosophical speculation. Calculations of the energy content of the universe show that matter, radiation, and dark energy provide positive contributions, while gravity provides negative ones. The accounting is not easy, because defining energy in general relativity is more complicated than in Newtonian mechanics. Energy can be localized for matter and radiation, but gravitational energy is spread out and not easily captured by a single number. Yet in cosmology, the overall concept of zero total energy is both meaningful and consistent with observations. The implications are profound. If the total energy of the universe is zero, then conservation laws are perfectly respected from the very beginning. The universe did not have to borrow energy from an outside source. It could arise naturally from a quantum fluctuation or a transition in a field with no violation of physics. In that sense, existence is not something purchased with energy, but something permitted by balance. This idea also connects to the broader theme of why the universe is comprehensible. Conservation laws are tied to symmetries, as shown by Noether's theorem. The invariance of physical laws across time and space guarantees conservation of energy and momentum. If the universe as a whole respects these symmetries, then the zero energy balance is not just an accident, but a reflection of those symmetries. The universe is allowed to exist because its existence does not break the rules. Skeptics point out that energy in general relativity is not always well defined, especially on cosmic scales. Unlike in Newtonian mechanics, where energy can be neatly separated into potential and kinetic, general relativity deals with curved space-time where local definitions of energy do not always add up globally. Some formulations argue that the total energy of the universe cannot be defined in a strict sense. But in practice, the zero-energy hypothesis remains useful because it captures the balance between positive and negative contributions and explains how the universe can be consistent with conservation from its earliest moments. Another layer of complexity arises with dark energy. This mysterious component, which drives the accelerated expansion of the universe, behaves differently from matter and radiation. It appears to be a property of space itself with uniform density. Whether it fits neatly into the zero-energy accounting is still debated. Some versions of the hypothesis incorporate dark energy as part of the balance, while others treat it as a separate issue. Either way, the principle of total balance remains a guiding idea. The possibility of a zero-energy universe also shapes how we think about cosmic origins. It suggests that the leap from nothing to something is not as large as it seems. If the total is zero, then the universe is not a violation of conservation, but a realization of it. The emergence of matter, light, and structure does not require an external source. It requires only that positive and negative contributions cancel. This does not explain why the laws of physics are the way they are, but it explains how existence is possible within them. In this sense, the zero-energy hypothesis is both bold and conservative. Bold, because it claims the universe costs nothing. Conservative, because it rests entirely on known principles of conservation. It does not invoke new forces or violations. It simply extends the logic of balance to the largest scale imaginable. It also opens questions. If the universe is exactly zero energy, is that true only on average or at every stage of evolution? Did the balance hold during inflation, during nucleosynthesis, during galaxy formation? If so, what mechanism ensured it? If not, how close is the balance, and what does any deviation mean? These are open research questions, pursued with observations of the cosmic microwave background, large-scale structure and gravitational waves. The hypothesis also connects to ideas about the multiverse. If inflation can produce many universes, each bubble may carry its own energy balance. If conservation requires total zero energy, then each universe must satisfy it. In this view, the zero-energy principle is not just a property of our universe, but of any possible universe. That universality would make it even more powerful as an explanation. The elegance of the idea lies in its simplicity. The universe, with all its complexity, might be the ultimate free lunch because the positive and negative energies cancel exactly. What looks like abundance is balanced by debt. What looks like existence is balanced by absence. Physics does not demand an external cause because the total remains unchanged. But the idea is not final. It is a working hypothesis, tested and refined as data improves. It may turn out that the balance is not exact, or that our understanding of gravitational energy must be revised. Yet the concept continues to guide thinking, because it aligns so naturally with what conservation laws suggest. And so, the zero-energy universe hypothesis becomes another step in the unfolding story. It shows that something from nothing is not paradoxical but permitted. It shows that the expansion of space, the growth of structure, and the presence of matter all fit into a balance. When physicists describe the universe at its most fundamental level, one of the words they return to again and again is symmetry. Symmetry in this context does not mean the visual balance of a butterfly's wings or the pleasing proportions of a crystal. It means that the laws of physics remain the same under certain transformations. If you rotate an experiment and repeat it, you get the same results. If you shift it from one place to another, the rules do not change. If you perform it today or tomorrow, the outcome is governed by the same principles. These symmetries are the foundation of conservation laws and the consistency of physics across the cosmos. But the universe we observe is not perfectly symmetrical. Electrons and protons exist, but we do not see equal numbers of positrons and antiprotons in everyday matter. 4 fundamental forces exist, but they are not equal in strength. Space is nearly uniform, but galaxies cluster into webs and voids. Symmetry appears to be broken. The puzzle is to understand how this happens, and the answer lies in a process called spontaneous symmetry breaking. To get a sense of what this means, imagine a perfectly balanced pencil standing on its point. In theory, the pencil is symmetrical. It could fall in any direction, but in practice it tips one way or another. The symmetry is broken not by the rules themselves, but by the outcome. The underlying physics allows all directions equally, but reality selects one. This is the essence of spontaneous symmetry breaking. The laws remain symmetrical, but the state of the system does not. In physics, this process occurs in fields that permeate the universe. The most famous example is the Higgs field. According to the Standard Model, particles acquire mass through their interactions with this field. In the early universe, the Higgs field was in a symmetric state, with no preferred value. As the universe cooled, the field settled into a particular value, breaking the symmetry. This choice was not forced by the equations, but by the dynamics of the field. Once it happened, particles gained mass, and the universe took on its current structure. The discovery of the Higgs boson in 2012 confirmed this picture. The boson is the quantum excitation of the Higgs field, evidence that the field exists and behaves as predicted. Without it, particles like quarks and electrons would remain massless, unable to form atoms. The breaking of symmetry by the Higgs field is thus essential to the existence of matter. Symmetry breaking also plays a role in unifying forces. At very high energies, such as those present in the early universe, the fundamental forces may have been unified. Electromagnetism and the weak nuclear force, for example, are distinct today. But at energies above a certain threshold, they merge into a single electro-weak force. As the universe cooled, the symmetry was broken and the forces separated. This process shaped the behavior of particles and interactions, determining how the universe evolved. The idea extends further. Grand unified theories suggest that at even higher energies, the strong force might also merge with the electro-weak force. If true, then the early universe was governed by a single symmetry that later broke into the 4 distinct forces we see now. Each breaking was spontaneous, a result of fields settling into particular values as the cosmos cooled. Each step reduced symmetry but increased structure, turning a simple beginning into the complex reality we observe. This pattern of breaking symmetry is not just a detail of particle physics, it has cosmological consequences. When symmetries break, they can leave behind relics such as domain walls or cosmic strings, depending on the details of the fields involved. These structures are hypothetical, but could leave observable signatures in the distribution of galaxies or the background of gravitational waves. Searching for such signatures is one way to test theories of symmetry breaking in the early universe. Symmetry breaking also helps explain why matter dominates over antimatter. In theory, the Big Bang should have produced equal amounts of both, but if that were the case, they would have annihilated, leaving only radiation. Instead, a small excess of matter remained, enough to build stars and planets. This asymmetry suggests that the laws of physics treat matter and antimatter slightly differently, a breaking of symmetry known as CP violation. Experiments have observed CP violation in certain particle decays, but not yet enough to fully explain the cosmic imbalance. The search for the source of this symmetry breaking continues. The concept of spontaneous symmetry breaking highlights the interplay between possibility and reality. The laws allow multiple outcomes, but the universe selects one. The outcome appears asymmetric, but the underlying rules remain symmetric. This duality is one of the reasons the universe is both comprehensible and diverse. Symmetry provides the framework, breaking provides the variety. To make the idea more tangible, consider another analogy. Imagine a perfectly round hilltop. A ball placed at the very top has complete symmetry. It could roll down in any direction equally. But as soon as it moves, the symmetry is broken. The hill has not changed, the laws governing motion have not changed, but the ball has chosen a direction, and the result is asymmetric. The Higgs field is like that hilltop. At high energies, it is balanced at the top. As the universe cools, it rolls into a particular value, and particles gain mass. The symmetry of the laws remains, but the state of the universe reflects a broken version of it. This breaking is what makes the universe rich in structure. Without it, matter might never clump, forces might never differentiate, and particles might remain massless. Symmetry provides the potential, but breaking symmetry provides the reality we inhabit. The study of symmetry and its breaking continues to guide research in both particle physics and cosmology. Experiments at particle accelerators probe how fields behave and how forces unify. Observations of the cosmic microwave background and large-scale structure test predictions about relics of early symmetry breaking. Theoretical models explore how different patterns of breaking could produce different universes. Each path reinforces the central role of symmetry in shaping existence. What makes this subject so striking is how it ties together scales. The Higgs field, acting at the quantum level, determines the mass of particles. That mass determines how atoms form. Atoms form molecules, molecules form structures, and structures form planets, stars, and life. The pattern of galaxies across the universe traces back to quantum fluctuations amplified by inflation, which itself depends on the behavior of fields and their symmetries. Every aspect of the cosmos, from the smallest particle to the largest cluster of galaxies, is linked through symmetry and its breaking. And yet, symmetry is not gone. It still governs the fundamental equations. Conservation of energy, momentum, and charge all rest on symmetries. The difference is that the universe we observe is the product of specific breakings layered upon those symmetries. What appears asymmetric is built upon symmetric laws. This understanding brings us closer to a deeper question. Are symmetries fundamental, or are they themselves emergent from something deeper? Could the symmetries we know be approximations, valid at our scales but breaking down at others? Could new symmetries await discovery, unifying forces or particles in ways not yet seen? These questions drive the search for physics beyond the standard model, including supersymmetry, string theory, and other frameworks. Supersymmetry, for example, proposes a symmetry between particles of matter and particles of force. If true, it would double the particle spectrum, pairing each known particle with a partner. Supersymmetry could solve puzzles like the nature of dark matter and the hierarchy of particle masses. It has not yet been observed, but the search continues because the idea of symmetry remains a powerful guide. The role of symmetry and its breaking is also central to theories of the early universe. Inflation itself may be driven by the dynamics of a field whose symmetry broke as the universe cooled. The distribution of galaxies may carry signatures of symmetry-breaking transitions. Even the vacuum energy that drives cosmic acceleration today may be linked to the structure of fields and their symmetries. Every major feature of cosmology connects directly or indirectly to this principle. So when physicists say that the universe is shaped by symmetry and spontaneous breaking, they are describing the deep logic of how structure emerges. The laws remain symmetric, but the outcomes break that symmetry, creating diversity. The particles, forces, and galaxies we see are the results of fields choosing specific states from many possibilities. The universe could have taken other forms, but the one we observe is the product of the particular breakings that occurred in its earliest moments. If symmetry and conservation define the rules of physics, then what happens to those rules without a universe to apply them to? When people imagine the beginning of the universe, they often picture a moment in time, a first tick of a cosmic clock. It feels natural to ask what happened before the Big Bang, or what caused it to occur. But when we bring physics into the picture, especially relativity and quantum theory, these questions become less straightforward. Time itself is not a backdrop that exists independently. It is part of the fabric of space-time, intertwined with space, matter, and energy. Near the beginning, when densities and energies were unimaginably high, the meaning of time and causality becomes uncertain. Understanding that region is one of the greatest challenges of cosmology. In Einstein's theory of general relativity, time is not absolute. It is affected by motion and gravity. A clock moving quickly runs more slowly relative to one at rest. A clock deeper in a gravitational field ticks more slowly than one farther away. Time is flexible, woven into the geometry of space-time. When cosmologists trace the universe backward, they follow this geometry. The equations show that as we move toward the Big Bang, density and curvature grow without limit. Extrapolated all the way, they reach a singularity, a point of infinite density and zero volume. At that point, the equations break down. Time itself, as described by relativity, seems to stop. But singularities are signs that a theory has reached its limits, not literal descriptions of reality. Physicists do not believe the universe was truly an infinitely dense point. Instead, they believe quantum effects must dominate at such scales. Quantum mechanics and relativity must be combined in a theory of quantum gravity to describe those conditions. Without such a theory, asking what happened before the Big Bang may not even make sense, because time itself may not extend into that region. This raises the question of causality. In everyday life, we assume that causes precede effects. Strike a match, and a flame appears. Drop a ball and it falls. This chain of cause and effect is built on the flow of time, but near the beginning, when time may not be well defined, what does causality mean? Can we speak of a cause for the universe if time itself emerged only with the universe? The question is subtle. If time is part of the universe, then the notion of before the universe is like asking what lies north of the North Pole. The question presumes a context that does not exist. Several proposals attempt to address this. One is the Hartle-Hawking no-boundary proposal, which suggests that near the beginning, time as we know it transforms into something more like space. In this view, the universe has no boundary in time, just as the surface of a sphere has no edge. Asking what came before is like asking what is south of the South Pole. The question loses meaning. Time emerges smoothly, and the need for a cause in the usual sense disappears. Another approach comes from models of quantum cosmology, which suggests the universe could arise from a quantum fluctuation of the vacuum. In such models, causality is not defined in the usual way, because the fluctuation does not occur within time. Instead, time itself is part of the transition. The universe does not begin in time, but with time. Causality in this sense is replaced by boundary conditions on the wave function of the universe. Even within inflationary theory, the role of time is nuanced. Inflation stretches quantum fluctuations into cosmic seeds, but inflation itself may be eternal into the future, and perhaps into the past in some models. In that case, the universe has no single beginning, but rather a branching structure of inflating regions giving rise to pocket universes. Time within each pocket has a beginning, but the overall multiverse may not. Whether such models are correct remains uncertain, but they show that causality near the beginning is not a settled matter. The difficulty lies in the fact that our intuition about time comes from low energy, everyday conditions. We experience a steady flow from past to future, marked by clocks and memory. But this flow is tied to the increase of entropy, the measure of disorder. The arrow of time we perceive is a result of the second law of thermodynamics. Entropy tends to increase. Near the beginning, when the universe was in a very low entropy state, the arrow of time itself may have been undefined. The future and past may not have been distinguished until the universe expanded and entropy began to grow. This perspective suggests that causality is not fundamental but emergent. At high energies and small scales, time may behave differently, and cause and effect may blur. At lower energies and larger scales, time acquires direction, and causality takes on the familiar form. If so, then the chain of cause and effect we rely on may itself be a product of cosmic evolution, not a principle that applies all the way back to the beginning. Experiments cannot yet probe these scales directly, but theoretical frameworks give hints. String theory, for example, proposes extra dimensions of space and perhaps new ways of describing time. Loop quantum gravity suggests that space-time itself is quantized with discrete units. In such models, the singularity of the Big Bang may be replaced by a bounce, where a previous contracting phase leads to expansion. If so, then time does extend beyond the Big Bang, but in a cyclical or oscillating form. Causality would continue, but in a broader framework than we currently imagine. Other approaches consider the universe as timeless at the fundamental level. The Wheeler-DeWitt equation, a candidate for describing the wave function of the universe, has no explicit time variable. In this view, time emerges only when subsystems interact, and causality is a derived concept. The universe at its most fundamental may be a static state, with time arising as an approximation for observers like us. What all these ideas have in common is that they challenge the notion of a clear beginning with a definite cause. They suggest that time and causality, rather than being universal absolutes, may themselves be products of the universe. Asking what caused the universe may be like asking what supports the Earth. It assumes a framework that the universe itself defines. This does not mean the questions are meaningless. It means the answers may not look like the cause and effect chains we are used to. They may involve boundary conditions, quantum states, or emergent properties. They may describe how time begins without requiring a cause in time. They may describe how causality is replaced by probability, with the universe arising not from a prior event, but from the rules of quantum mechanics applied to space-time itself. The recognition that time and causality are uncertain near the beginning also shapes how we think about observation. The cosmic microwave background gives us a snapshot from about 380,000 years after the Big Bang. Beyond that, light cannot travel freely, so we cannot see directly. Inflation provides indirect evidence for conditions earlier still, through the pattern of fluctuations, but the first fraction of a second remains hidden, accessible only through theory. The challenge is to connect those theories to observable consequences, such as gravitational waves or signatures in the distribution of galaxies. In this way, the study of time near the beginning is not just philosophical but scientific. It guides experiments, suggests what to look for, and frames the interpretation of data. It links cosmology to particle physics, quantum mechanics to relativity, and observation to theory. Each step brings us closer to understanding how time itself may have emerged, and how causality may have arisen as the universe cooled and expanded. The questions remain open. Does time have a beginning? Or does it extend eternally? Is causality fundamental, or does it emerge from deeper rules? Is the universe a single event or part of a larger structure? Each possibility carries profound implications, not only for science but for how we understand existence. When we trace the expansion of the universe backward in time, following the equations of general relativity, we find that distances shrink, densities rise, and temperatures soar. Every step closer to the beginning brings us to a smaller, hotter, denser cosmos. Extrapolated far enough, the equations point to a singularity, a state where density becomes infinite, curvature becomes infinite, and the fabric of space-time itself collapses into a point of no size. In this state, the mathematics stops working. The predictions lose meaning. Physicists describe this as the point where physics breaks down. The word singularity can give the impression of something tangible, a real object lurking at the heart of the cosmos. But it is better understood as a signal that our theories have reached their limits. General relativity is extraordinarily successful at describing gravity on large scales, from planets to galaxies to black holes. Yet it is a classical theory, meaning it does not include quantum effects. At extreme densities, where space-time itself is subject to quantum uncertainty, relativity alone is not enough. The singularity is not necessarily a physical point that exists. It is the place where our equations fail to describe reality. This is not unique to cosmology. In physics, singularities often appear when theories are pushed beyond their valid range. For example, the equations describing fluid flow can predict infinite density at a shock wave, but in reality, molecular effects prevent such infinities. The equations are an approximation, and their limits show where a deeper theory is needed. The cosmological singularity is the same. It is a pointer, telling us that relativity must be replaced or extended by a theory that includes quantum mechanics. The presence of singularities is built into general relativity itself. The singularity theorems of Stephen Hawking and Roger Penrose showed that under broad conditions, a universe with matter and gravity must contain singularities, either in the past or the future. In black holes, this appears as the central singularity inside the event horizon. In cosmology, it appears as the Big Bang singularity at the origin of time. These theorems do not prove that singularities are real, but they prove that relativity inevitably predicts them. The only way around them is to go beyond relativity. At the singularity, not only do densities diverge, but the concept of time itself breaks down. In relativity, time is part of space-time. If space-time collapses into a point, then time does not extend beyond it. Asking what happened before becomes meaningless within the framework of relativity. This is one reason why cosmologists are cautious about describing the singularity as the literal beginning of the universe. It is more accurate to say that the universe, as described by relativity, cannot be extended beyond that point. What lies beyond requires a new theory. One candidate for that new theory is quantum gravity, the unification of general relativity and quantum mechanics. Several approaches are being pursued. String theory suggests that the fundamental constituents of reality are not point particles, but tiny strings vibrating in multiple dimensions. At very high energies, these strings spread out the interactions, avoiding infinities. In this framework, the singularity may be replaced by a finite, well-behaved state. Loop quantum gravity takes another approach, proposing that space-time itself is quantized, composed of discrete units of area and volume. In this picture, space-time cannot collapse to zero size because there is a smallest unit. Instead of a singularity, the Big Bang may have been a bounce, where a previous contracting universe reached a minimum size and then rebounded into expansion. This replaces the breakdown of physics with a continuation through a new phase. Other models suggest that the singularity may be smoothed out by effects of vacuum energy, higher dimensions, or new states of matter. In all cases, the aim is the same, to replace the infinity with a finite description. The singularity is not a place where the universe truly began, but a marker of our incomplete knowledge. The breakdown at the singularity is not just a theoretical problem, it has practical consequences for how we interpret observations. When we look at the cosmic microwave background, we see the universe as it was about 380,000 years after the Big Bang. Inflation pushes our knowledge back much further, to a fraction of a second. But the singularity lurks even earlier, preventing us from describing the true initial state. Without a theory beyond relativity, we cannot say what conditions were like at time zero. Our models begin slightly after, once expansion was already underway. This limitation forces humility. The Big Bang model is not a theory of absolute origin. It is a theory of evolution from a hot, dense state. The singularity is the boundary of that description, the place where we hand the problem to future physics. Some physicists hope that quantum gravity will provide a complete picture, extending our knowledge past the singularity. Others suspect that the concept of an absolute beginning may itself be misguided, replaced by cycles, bounces, or eternal inflation. In all cases, the singularity remains a reminder that current physics is incomplete. Black holes provide another perspective. At their centers, general relativity predicts singularities as well. Matter collapses without bound, curvature diverges, and space-time ends. But just as with the Big Bang, physicists believe the singularity is a sign of breakdown, not a real physical object. Quantum effects must intervene, preventing true infinities. Understanding black hole singularities and cosmological singularities may require the same new theory of quantum gravity. They are two sides of the same problem, the clash between relativity and quantum mechanics. This is why research into black holes has become so important for cosmology. Processes like Hawking radiation, where quantum effects allow black holes to emit radiation, point toward the interplay of gravity and quantum mechanics. The information paradox, which asks whether information swallowed by a black hole is lost forever, pushes this interplay even further. Solving these puzzles may illuminate not only the nature of black holes, but also the nature of the Big Bang singularity. The breakdown of physics at the singularity is not a failure of science, but an opportunity. It marks the boundary where known theories meet the unknown, where predictions give way to questions. Every advance in theoretical physics has come from probing such boundaries. The singularity at the beginning of the universe is perhaps the most profound boundary of all. It also shapes how we think about causality and origin. If the singularity is not a real state but a marker of incomplete theory, then asking what caused the universe may be asking a question that presumes too much. Cause and effect require time, and time may not exist beyond the singularity. What replaces it may not be a cause in the usual sense, but a set of conditions or a quantum state from which time itself emerges. The singularity is thus both a problem and a guide. It tells us that relativity works but not forever, that quantum mechanics works but not for space-time, and that a deeper synthesis is required. It drives the search for unification, for a theory that does not break down at the beginning. In this sense, the singularity is not just a feature of equations, but a challenge to our understanding of reality. It reminds us that the universe is stranger than our current theories can describe. It invites us to imagine new frameworks, new mathematics, and new ways of thinking about existence. When physicists confront the singularity at the beginning of the universe, or the singularity predicted inside black holes, they know they are facing the limits of general relativity. Relativity describes gravity as the curvature of space-time, and it works beautifully at large scales, from planets and stars to galaxies and the entire observable cosmos. But relativity does not include quantum mechanics, the set of rules that governs particles and forces at small scales. Whenever matter is compressed to extreme densities, quantum effects cannot be ignored. This means that at the most fundamental level, a complete description of the universe requires a theory of quantum gravity, a framework that unifies relativity and quantum mechanics into a single consistent whole. Finding such a theory has proven extraordinarily difficult. Relativity and quantum mechanics rest on different foundations. Relativity treats space-time as smooth and continuous, while quantum mechanics insist on discreteness and uncertainty. Relativity is deterministic, while quantum mechanics is probabilistic. Reconciling these differences requires rethinking what space-time itself might be. Out of this challenge have come several approaches, but two of the most developed are string theory and loop quantum gravity. String theory begins with a simple but radical idea that the fundamental building blocks of nature are not point particles but tiny vibrating strings. These strings can vibrate in different modes, and each mode corresponds to a different particle. A photon, an electron, or a quark are all different vibrations of the same kind of string. This idea unifies matter and forces, since both arise from the same underlying entities. Importantly, string theory naturally includes a particle with the properties of the graviton, the quantum carrier of gravity. In this way, gravity is built into the framework from the start. The mathematics of string theory requires extra dimensions of space. Instead of the familiar 3, string theory suggests there may be 9 or more, compactified into tiny shapes too small to observe directly. These extra dimensions give strings room to vibrate in ways that generate the variety of particles we see. They also provide the richness needed to connect quantum mechanics with gravity. Though the extra dimensions are hidden from direct view, their geometry influences the properties of particles, linking cosmology to the shape of space at the smallest scales. String theory also replaces the singularity with new possibilities. Because strings have finite size, they smear out interactions that would otherwise produce infinities. At very high energies, where point particles would lead to breakdowns, strings remain well behaved. This means that the Big Bang singularity or the center of a black hole may not be true infinities, but regions where stringy effects dominate, smoothing out the physics. Some models suggest that the Big Bang was not the beginning, but a collision of higher dimensional branes in a larger space. Others suggest cycles of expansion and contraction, with strings mediating the transitions. In each case, the singularity is replaced by a finite, describable process. Loop quantum gravity takes a different path. Instead of adding new dimensions or entities, it starts by applying quantum principles directly to space-time. In this approach, space-time itself is quantized, made of discrete units of area and volume. Just as matter is made of atoms, space may be made of fundamental chunks. These chunks are connected in networks of loops, forming a spin network that evolves over time into a spin foam. Geometry is no longer continuous but granular. This discreteness has profound consequences. It means that space-time cannot be subdivided infinitely. There is a smallest unit, a quantum of space, beyond which division is meaningless. At the Planck scale, about 10⁻⁵ meters, the smoothness of relativity gives way to a granular structure. This prevents the collapse to a singularity, because space-time cannot shrink below its fundamental unit. Instead of infinite density, loop quantum gravity predicts a bounce. The universe may have contracted to a minimum size before rebounding into expansion, replacing the Big Bang with a big bounce. Loop quantum gravity has been applied to black holes as well. Instead of a singularity at the center, the collapse may lead to a core of finite density, where quantum geometry resists further compression. Matter and information may not be lost but transformed, preserving consistency with quantum principles. These results are still under development, but they illustrate how quantizing space-time changes the picture fundamentally. Both string theory and loop quantum gravity aim to solve the same problem, but they do so in very different ways. String theory introduces new dimensions, unifies particles and forces, and provides a framework rich enough to encompass all interactions. Loop quantum gravity keeps space-time central, quantizing it directly without extra entities. Each approach has strengths and weaknesses. String theory is mathematically powerful and connects naturally with particle physics, but it requires assumptions that are hard to test, such as extra dimensions. Loop quantum gravity is more minimal and background independent, but it struggles to incorporate matter and unification as fully as string theory. Despite these differences, both share the goal of removing singularities. They both suggest that space-time has a structure at small scales that prevents infinities. They both suggest that the breakdown of physics at the beginning is not the end of explanation, but a sign that a deeper theory is needed. They both aim to replace the unknown with a describable, testable framework. Testing these theories is challenging, because the scales at which quantum gravity becomes important are far beyond direct experiments. But indirect tests may be possible. The cosmic microwave background could contain imprints of quantum gravity in its polarization or fluctuation spectrum. Gravitational waves could carry signatures of physics from the earliest moments. Black hole evaporation could reveal hints of quantum gravity in the way information is preserved. Each of these is a frontier of research, linking theory with observation. The search for quantum gravity is not only about solving singularities, it is also about unifying the two great frameworks of modern physics. Quantum mechanics describes the small, relativity describes the large. A complete theory must describe both because the universe contains both. The earliest moments of the cosmos, when densities were extreme, require both. Black holes, where gravity and quantum effects collide, require both. Without quantum gravity, our picture remains incomplete. And yet, even in their incompleteness, string theory and loop quantum gravity offer glimpses of what a deeper reality might look like. Strings vibrating in hidden dimensions suggest a universe far richer than the one we see. Loops of quantum geometry suggest that space itself has an atomic structure. Both show that the familiar concepts of space and time may be emergent, approximations of something more fundamental. The fabric of reality may not be smooth at all, but woven from deeper threads or loops. This recognition pushes us to think differently about beginnings. If space-time is emergent, then asking what happened before the Big Bang may not make sense in the usual way. What we call the beginning may be a transition, a phase change in deeper structures. What we call singularities may be artifacts of incomplete theories, replaced by finite processes in the correct framework. The universe may have a history that extends beyond what relativity alone can describe. The pursuit of quantum gravity is ongoing, and neither string theory nor loop quantum gravity has yet provided definitive answers. Each continues to evolve and new approaches may emerge. But together, they show that the breakdown of physics at singularities is not a wall, but a doorway. It is an invitation to develop new ways of describing reality, new mathematics, and new insights into how the universe works. When physicists think about the beginning of the universe, they quickly run into the question of boundaries. In classical cosmology, time seems to begin at the Big Bang, where relativity points to a singularity of infinite density. At that singularity, physics ceases to describe what happens, and the natural question arises, what lies before it, or what caused it? But this question assumes that time behaves as we are used to, stretching smoothly backward like a line. Stephen Hawking and James Hartle proposed an alternative, one that reshapes how we think about beginnings. Their no-boundary proposal suggests that time itself may change character near the start, and that the universe may have no edge or boundary in time at all. To appreciate this, it helps to remember how relativity describes space-time. In our everyday experience, time is different from space. We can move back and forth in space, but time flows forward. The equations of relativity reflect this difference by assigning a different mathematical sign to the time dimension. But in quantum mechanics, under certain conditions, it can be useful to treat time more like a spatial dimension. This trick, known as imaginary time, turns time into something that behaves mathematically like space. Hartle and Hawking used this idea to describe the early universe. They suggested that near the beginning, time did not behave like ordinary time but like space. Instead of a sharp boundary at a singularity, the universe could be described as smoothly rounded, like the surface of a sphere. Just as a sphere has no edge, you can travel around it endlessly without finding a border. The universe in this picture has no temporal edge. Asking what came before is like asking what is south of the South Pole. The question presumes a direction that does not exist. In this way, the no-boundary proposal avoids the singularity. There is no point of infinite density, no edge where physics breaks down. Instead, the universe emerges smoothly, with time gradually taking on its familiar character as the cosmos expands. At first, all dimensions are space-like. Then one direction evolves into what we experience as time. The Big Bang is not a point of origin, but a transition in the geometry of space-time. This idea is expressed mathematically in the Hartle-Hawking wave function of the universe. In quantum mechanics, systems are described by wave functions that encode probabilities. The wave function of the universe would describe the probabilities of different possible geometries and histories. The no-boundary condition specifies that the wave function is defined only on smooth, compact geometries without boundaries. In other words, the universe's quantum state is one that has no edge in time. The consequences of this proposal are striking. It means the universe does not need a cause in the usual sense, because time itself does not extend beyond the no-boundary state. The question of what happened before the Big Bang is reframed, because there is no before. The universe simply is, with its history described by probabilities in the wave function. The no-boundary proposal replaces the concept of a beginning with the concept of a smooth emergence. This does not mean the universe is arbitrary. The Hartle-Hawking wave function predicts which histories are more likely, favouring universes that are large and smooth over those that are small and chaotic. In this way, the proposal explains why our universe is nearly uniform on large scales, and why it underwent inflation. The no-boundary condition naturally leads to inflationary expansion, providing a mechanism for the observed structure of the cosmos. The proposal also connects relativity and quantum mechanics in a novel way. Relativity provides the geometry of space-time. Quantum mechanics provides the probabilities of different geometries. The no-boundary condition unites them, showing how the universe can be described without singularities or edges. It is one of the most ambitious attempts to apply quantum principles to the cosmos as a whole. Critics of the proposal point out that it is difficult to test directly. The wave function of the universe is not something we can measure in a laboratory, but it can make predictions about the properties of the cosmic microwave background and the distribution of fluctuations. In this sense, it connects abstract mathematics to observable quantities. Cosmologists have studied whether the no-boundary condition leads to the patterns we see in the sky, and while debate continues, the idea remains a compelling framework. It is also important to clarify what the proposal does not claim. It does not say the universe appeared from literal nothing. It does not deny the laws of physics. Instead, it provides a boundary condition for those laws, specifying how the universe's history is described in quantum terms. The no-boundary proposal is not about replacing physics with metaphysics, but about extending physics to the earliest possible domain. One of the elegant aspects of the idea is its simplicity. By replacing a singularity with a smooth geometry, it removes infinities and inconsistencies. By treating time as space-like near the beginning, it removes the need for a first moment. By using quantum mechanics, it replaces determinism with probabilities, allowing the universe's history to emerge from the wave function. Each step is consistent with known principles, yet together they produce a radically new picture of beginnings. The no-boundary proposal also highlights the role of imagination in physics. To think of time as imaginary, to picture the universe as a four-dimensional surface without edges, is to move beyond intuition, but physics often requires such steps. Relativity asked us to accept that time dilates and space contracts. Quantum mechanics asked us to accept that particles behave as waves. The no-boundary proposal asks us to accept that beginnings may not exist in the way we imagine. This perspective does not eliminate questions but reframes them. Instead of asking what caused the universe, we ask what the wave function allows. Instead of asking what came before, we ask what conditions describe the no-boundary state. Instead of seeking an external cause, we seek internal consistency. The universe does not need a reason to begin because, in this picture, beginning is not a meaningful concept. Some versions of the proposal also suggest that multiple histories coexist in the wave function, with different probabilities. This connects to the idea of the multiverse, where many possible universes exist, each realized in different branches of the wave function. Our universe is then one outcome among many, selected not by necessity but by probability. The no-boundary condition provides the framework for such a multiverse, where diversity arises naturally from quantum principles. Whether or not this is the final word, the no-boundary proposal has influenced how physicists think about the earliest moments. It shows that singularities are not inevitable. It shows that time itself may be emergent, changing character near the beginning. It shows that quantum mechanics can be applied not only to particles but to the universe as a whole. And just as important, it shows that the deepest mysteries can be approached with the same tools that describe the everyday. The mathematics of wave functions and geometry, extended to the cosmos, provide a way to talk about origins without abandoning science. The universe may be strange, but it is not beyond description. When we imagine the universe beginning with a singularity, the image is stark, everything compressed into an infinitesimal point, emerging suddenly into expansion. It feels absolute, like a once-and-for-all event. But not all cosmological models require this picture. Some suggest that the universe may not have begun at all in the sense of a single origin. Instead, it may have passed through cycles, or bounced from a previous phase of contraction into expansion. These alternative models challenge the idea of a single beginning, and replace it with a history that stretches further back, perhaps indefinitely. The idea of a cyclic universe has deep roots. Ancient philosophers imagined time as a circle rather than a line, with the cosmos eternally repeating patterns of birth, death, and rebirth. In modern physics, the notion has been revived in new forms, supported not by mythology, but by attempts to avoid singularities and to connect cosmic history with quantum principles. The simplest version is the bouncing universe. In this picture, the expansion we see today was preceded by contraction. The universe shrank under its own gravity, reached a minimum size, and then bounced outward into expansion. Instead of a singularity, there is a turnaround point where new physics prevents collapse to infinite density. Loop quantum gravity provides one mechanism for such a bounce. In this approach, space-time is quantized, with discrete units of area and volume. When densities reach the Planck scale, quantum geometry creates a repulsive effect that resists further compression. Instead of continuing to shrink, the universe rebounds. This replaces the singularity with a bounce, allowing time to extend smoothly through the transition. Our expanding universe is then the result of a previous contracting one. The cycle may be one time or may repeat endlessly, depending on the details. Another class of models considers cyclic universes driven by the dynamics of fields and extra dimensions. In some string theory frameworks, our universe is envisioned as a three-dimensional brane embedded in a higher dimensional space. Collisions between branes can trigger expansions like the Big Bang. If such collisions happen repeatedly, the universe undergoes cycles of expansion and contraction. Each cycle begins with a hot dense state, evolves into structure, and ends in contraction before the next collision. Time in this picture extends infinitely, with no first cycle. Cyclic models offer ways to address puzzles that inflation solves. For example, they can explain why the universe is uniform on large scales, because each cycle has time to smooth out irregularities before the next begins. They can also explain flatness, because repeated cycles can drive the geometry toward balance. In this sense, cyclic universes provide an alternative to inflation, offering different mechanisms for the same observations. One appeal of bouncing and cyclic models is that they remove the need for a singular beginning. Instead of physics breaking down at infinite density, new principles intervene. Quantum effects, extra dimensions, or novel fields prevent collapse. The universe may be eternal in time, with no absolute starting point. What we call the Big Bang is then just the latest in a series of transitions. These ideas also raise new questions. If the universe bounces or cycles, what determines the properties of each cycle? Do they repeat identically, or does each cycle differ? If they differ, could earlier cycles have had different physics, different constants, or different structures? Could information pass from one cycle to the next, leaving imprints we could detect? Some models suggest that traces of previous cycles could appear in the cosmic microwave background as unusual correlations or patterns. Searching for such signatures is one way cosmologists test the plausibility of these ideas. There are also challenges. For a cyclic model to work, entropy must be managed. The second law of thermodynamics says entropy increases over time. If each cycle adds entropy, then after infinite cycles the universe would reach a state of maximum disorder, unable to restart. To avoid this, models must find ways to reset or dilute entropy, often through expansion phases that spread it out. Inflation provides one mechanism, and cyclic models must offer alternatives. Despite these challenges, the possibility of a bouncing or cyclic cosmos remains compelling. It avoids the singularity, extends history beyond the Big Bang, and connects cosmic evolution to deeper principles. It shows that the universe we see may be one chapter in a much longer story, one expansion among many. From the observational side, cosmologists look for evidence that could distinguish between inflation and cyclic models. The spectrum of fluctuations in the cosmic microwave background, the distribution of galaxies, and the properties of gravitational waves all provide clues. While inflation currently fits the data best, cyclic models are not ruled out, and some versions remain consistent with observations. The debate continues, with each new measurement refining the possibilities. These models also connect to philosophical questions. If the universe is cyclic, then does it ever truly begin? If it has always existed, cycling endlessly, then the question of origin shifts. Instead of asking why the universe began, we ask why the cycles exist. Instead of a singular event, we face an eternal process. This reframing changes how we think about existence, replacing beginnings with continuities. It is important to emphasize that these ideas are not outside science. They are grounded in mathematics, tested against observations, and refined through predictions. They may sound exotic, but they arise from the same drive to extend physics beyond the limits of current theories. Just as inflation grew from attempts to solve puzzles in the Big Bang model, bouncing and cyclic universes grow from attempts to avoid singularities and connect quantum physics with cosmology. One fascinating feature of cyclic models is how they can incorporate ideas from both relativity and quantum mechanics. Relativity governs the large-scale contraction and expansion. Quantum mechanics provides the mechanism to prevent singularities. Together, they create a cosmos that oscillates rather than collapses. This interplay highlights the need for unification, the same need that drives string theory and loop quantum gravity. In this sense, bouncing and cyclic universes are not competitors to other approaches but companions. They explore different possibilities within the same search for quantum gravity. They remind us that our picture of the universe is provisional, and that multiple paths may lead to answers. When astronomers first detected the faint glow of the cosmic microwave background in 1965, it seemed like little more than an annoyance. Arno Penzias and Robert Wilson were trying to eliminate a source of static from their radio antenna in New Jersey, cleaning out bird droppings and checking circuits to no avail. But the noise remained, uniform in every direction. What they had stumbled upon was not interference at all, but the afterglow of the Big Bang itself, the radiation left over from when the universe was only a few 100,000 years old. That discovery confirmed one of the strongest predictions of the hot Big Bang model, and gave scientists a window into the earliest observable era of the cosmos. Since then, the cosmic microwave background, often shortened to CMB, has become one of the most powerful tools for testing physics at the very edge of knowledge. To see why, it helps to remember what the CMB represents. In the early universe, temperatures were so high that matter existed as a plasma of protons, electrons, and photons. Photons scattered constantly off free electrons, preventing light from travelling freely. The universe was opaque, like the interior of a star. As expansion continued, the plasma cooled. When the temperature dropped to about 3000 Kelvin, electrons combined with protons to form neutral hydrogen. Suddenly, photons were no longer trapped. They could stream through space largely unimpeded. This moment, called recombination, released a flood of radiation that still fills the universe today. As expansion stretched its wavelength, that radiation cooled into the microwave part of the spectrum. Every direction we look, we see this relic glow, nearly uniform but carrying faint imprints of the conditions at the time. The uniformity is striking. The CMB has the same temperature to within 1 part in 100,000 across the sky. This shows that the early universe was extraordinarily smooth on large scales, consistent with the predictions of inflation. But within that smoothness are tiny variations, fluctuations in temperature that correspond to slight differences in density. These fluctuations are the seeds from which galaxies grew. Mapping them with precision allows scientists to test theories of the early universe with exquisite accuracy. The first detailed map came from the COBE satellite in the early 1990s. COBE showed that the fluctuations existed and matched the scale predicted by theory. The discovery won the Nobel Prize and launched a new era of precision cosmology. Later missions, such as DUMAP and Planck, refined the measurements, producing maps of the CMB with resolution so fine that they revealed the detailed statistical properties of the fluctuations. These properties encode information about the universe's contents, geometry, and history. One of the key results from the CMB is confirmation of the flatness of the universe. The angular scale of the fluctuations depends on the geometry of space. If space were strongly curved, light paths would bend, and the apparent size of fluctuations would change. Planck's data show that the geometry is flat to within a small margin, consistent with the predictions of inflation and with the idea that the total energy of the universe is balanced. The CMB also provides a cosmic census. By analysing the spectrum of fluctuations, scientists can determine the proportions of ordinary matter, and dark energy. The results show that ordinary matter makes up only about 5% of the total. Dark matter accounts for about 27%, and dark energy dominates with about 68%. These numbers come not from local observations, but from the largest possible scale, written into the faint variations of the CMB. Even more remarkably, the CMB carries imprints of sound waves in the early universe. Before recombination, matter and radiation were coupled, and density fluctuations set up oscillations like ripples in a pond. These acoustic waves left peaks and troughs in the pattern of CMB fluctuations. The positions and heights of these peaks match the predictions of theory and provide another way to measure cosmological parameters. The agreement between observation and theory is one of the great triumphs of modern physics. But the CMB does more than confirm existing models. It also tests ideas about what happened in the first fractions of a second. Inflation predicts a specific spectrum of fluctuations, nearly scale invariant, meaning that fluctuations look similar across different sizes, with only slight deviations. Planck's data show exactly this pattern, matching inflation's predictions. Inflation also predicts a certain distribution of phases and correlations, which are seen as well. These results give strong support to the idea that inflation occurred, stretching quantum fluctuations into cosmic seeds. There are still puzzles. Inflation also predicts the possibility of primordial gravitational waves, ripples in space-time generated during the rapid expansion. These would leave a signature in the polarization of the CMB, specifically a swirl pattern known as B-modes. Experiments have searched for this signal, and while hints have appeared, no definitive detection has been made. If found, such a signal would be direct evidence of inflation and of quantum gravity effects in the earliest universe. The search continues with increasing sensitivity, making the CMB a laboratory for physics at energies far beyond any particle accelerator. The CMB also offers clues about dark matter and dark energy. While it does not reveal their nature directly, it shows their influence on the growth of fluctuations and the geometry of space. By combining CMB data with galaxy surveys and supernova observations, cosmologists can pin down their properties more tightly. The fact that the results are consistent across different methods strengthens confidence in the picture. Another intriguing possibility is that the CMB could contain signatures of physics beyond the standard model. If there were additional fields, topological defects, or exotic particles in the early universe, they could leave imprints in the fluctuations. Subtle deviations from the predicted patterns might reveal new physics. Searching for such deviations is an active area of research. The CMB also serves as a test of isotropy and homogeneity. The cosmological principle assumes that the universe is the same in all directions on large scales. The CMB largely supports this, but there are small anomalies, such as an alignment of low multipoles, sometimes called the axis of evil. Whether these are statistical flukes or hints of deeper physics remains uncertain. They remind us that even with high precision, mysteries remain. What makes the CMB so powerful is that it connects us directly to the earliest observable era. It is not light from stars or galaxies, but from the universe itself when it was only a few 100,000 years old. It carries information about conditions that existed long before galaxies formed. It bridges cosmology with particle physics, linking the largest scales to the smallest. In this way, the CMB is not just a relic but a tool. It is the closest thing we have to a fossil record of the universe's infancy. By studying it, we can test theories of inflation, measure fundamental constants, and search for traces of new physics. Every refinement in measurement brings new insights, and every anomaly brings new questions. The CMB also illustrates how observations can transform our understanding. What began as static in a radio antenna became the cornerstone of cosmology. Careful measurements turned it from a curiosity into a precision probe. Today, it stands as one of the strongest pieces of evidence for the Big Bang and as a laboratory for testing the physics of the earliest moments. When we follow the story of the universe from its present state back through billions of years of expansion, cooling, and structure formation, we reach a series of milestones. Galaxies forming out of fluctuations, light elements created in the first minutes, photons decoupling to produce the cosmic microwave background, and inflation stretching quantum noise into the seeds of structure. Beyond that lies the domain where space-time itself becomes uncertain, where singularities and quantum gravity await. Each step takes us closer to the deepest question: why is there something rather than nothing? Physics can describe how matter behaves, how space-time evolves, and how energy balances, but the question of why existence itself occurs pushes us to the edge of knowledge. When physicists talk about nothing, they do not mean an absolute void. In quantum field theory, what appears empty is full of activity. Fields fluctuate, virtual particles appear and vanish, and energy can be temporarily borrowed within the limits of the uncertainty principle. The vacuum is not nothing but a dynamic state with structure. Even the fabric of space-time carries geometry and energy. In this sense, physics shows that what we call nothing is already something, a foundation with properties that permit further creation. The possibility that the universe arose from such a vacuum is not a violation of conservation laws. If gravity carries negative energy, then the positive energy of matter and radiation can be balanced. The total energy of the universe may be zero, consistent with conservation. In this view, the universe is not a free creation but a balanced fluctuation, permitted by the symmetries of physics. Existence does not require energy from outside. It emerges naturally within the rules. But this leaves us with further questions. Why do the rules exist? Why do the laws of physics take the form they do, allowing fluctuations, fields, and balance? Could the laws themselves have arisen from a deeper structure, or are they fundamental? Physics can trace the history of the cosmos back to fractions of a second after the Big Bang, but the origin of the laws themselves is harder to place within science. Still, reflecting on how far physics has carried us is part of understanding what it means to ask why there is something. Consider how much of what we take for granted depends on subtle balances. If the density of the universe had been slightly different, it might have collapsed back or expanded too quickly for galaxies to form. If the strength of forces were different, atoms might not exist. If the cosmological constant were larger, expansion would prevent structure. The fact that the universe allows stars, planets, and life suggests that its properties are finely tuned. Some see this as evidence of deeper principles, others as evidence of a multiverse in which many universes exist with different properties, and we inhabit one that allows complexity. The question of nothingness also depends on how we define it. If by nothing we mean absence of matter, then the quantum vacuum shows how matter can arise without contradiction. If by nothing we mean absence of space-time, then proposals like the no-boundary idea show how time itself may emerge smoothly, without a singular beginning. If by nothing we mean absence of laws, then we reach the deepest level, one that physics has not yet addressed fully. Each definition of nothing leads to different reflections, and each shows that the boundary between nothing and something is not simple. Even so, physics has revealed that the universe is not arbitrary. Its structure follows rules, and those rules connect the smallest scales to the largest. Quantum fluctuations shaped galaxies. Symmetry breaking gave particles mass. Conservation allowed balance. Inflation stretched the fabric of space. Each step is lawful, not chaotic. The cosmos is not random noise, but a pattern consistent with principles. This consistency suggests that whatever nothing might mean, it is not absolute emptiness, but a context with potential. Reflecting on these ideas, one sees that the question of why there is something cannot be answered in the same way as questions about how matter behaves. It is a question that blends science with philosophy. Physics can show how something arises from what seems like nothing, how balance allows existence without contradiction, and how laws extend smoothly back. But whether those laws themselves must exist, and why they exist in this form, remains open. At the same time, reflecting on the story of physics provides perspective. The fact that humans on a small planet orbiting an ordinary star can map the cosmic microwave background, measure the expansion of space, and theorize about the origin of time itself is itself remarkable. It shows that existence not only permits complexity, but permits understanding. The universe is not only something, but something comprehensible. This raises another reflection. Perhaps the question of why there is something is inseparable from the fact that we are here to ask it. If universes exist where nothingness is true, then no one asks questions. In universes like ours with balance, structure and laws, questions are possible. The very act of reflection may be part of the explanation, not because our thoughts cause existence, but because existence that allows thought is the one we can experience. Yet physics continues to push the boundary further. Each advance in observation, each refinement in theory, brings us closer to understanding how the universe emerged. The CMB reveals the infant cosmos. Gravitational waves may reveal inflation. Particle physics probes the Higgs field and symmetry breaking. Black holes test quantum gravity. Each clue narrows the space between nothing and something, showing that the divide is less absolute than it seems. The reflections also remind us of humility. Just as earlier generations believed the Milky Way was the whole universe, or that time was absolute, we may find that our concept of nothing is limited. Future theories may show that what we call nothing is a special case of something deeper, just as space and time turned out to be aspects of space-time. Perhaps laws themselves will be shown to emerge from a more fundamental framework. If so, the mystery of why there is something will be reframed again. The fact that physics can even approach the question is itself progress. A century ago, the idea of the Big Bang was speculative. Half a century ago, inflation was new. Today, both are supported by evidence, and theories extend even further. What once seemed beyond science has become part of it. reflections on nothingness may follow the same path, moving from philosophy to physics as our understanding deepens. As we continue to reflect, one thing becomes clear. The universe is not only vast and ancient, but balanced and structured. Its history is not only long, but intelligible. The question of why there is something rather than nothing may not yet have a complete answer, but the journey toward that answer enriches our understanding of both physics and existence. And with that, the story continues. From quantum fluctuations to galaxies, from conservation laws to symmetry breaking, from inflation to the CMB, each step brings us closer to the edge of knowledge. Beyond that edge lies the mystery of nothingness, a mystery that may eventually be drawn into physics itself. The reflections do not close the book, but open it further, inviting more questions, more observations, and more ways of thinking about why there is something at all. When we arrive at the present, after tracing the universe back through its deep history and following it forward into open questions, we find ourselves reflecting not only on cosmology, but on the way knowledge itself grows. Each part of the story, from the earliest moments of inflation to the cosmic microwave background, from symmetry breaking to the role of conservation, shows how science approaches mysteries without needing to resolve them all at once. The universe, as we see it, is the product of laws that remain consistent across time and space, and of processes that link the very small to the very large. Every observation adds another layer. The faint glow of the microwave background tells us that the cosmos was once hot, dense, and nearly uniform. The clustering of galaxies tells us that quantum fluctuations were stretched into seeds of structure. The accelerating expansion tells us that vacuum energy is real, and that space-time itself can drive cosmic change. Each clue reveals that what we call nothing has properties, and that those properties are enough to make something possible. The reflections do not bring closure but invite continuity. We can trace the path of the cosmos back to tiny fractions of a second, but we cannot yet say what lies beyond the boundary where relativity and quantum mechanics clash. We can describe how conservation permits a zero-energy universe, but we cannot yet explain why the laws have that form. We can propose models of no boundaries, bounces, or cycles, but we cannot yet test them fully. Instead of closing questions, physics continues to open them, each step making the picture both clearer and more expansive. Even the act of telling this story is part of the process. By describing how the universe might arise from balance, how time might emerge, or how symmetries might break, we build frameworks for thought. These frameworks can be refined, tested, and corrected. What begins as speculation becomes theory, and what begins as theory becomes evidence, as observations confirm or refute predictions. The history of cosmology shows that progress does not require final answers, only steady inquiry. In this way, reflecting on why there is something rather than nothing becomes less about a single solution and more about participation in the unfolding of knowledge. Each generation adds to the account, drawing lines further into the unknown. Each observation gives a clearer view, yet each also reveals new mysteries. The question of nothingness, of origins, of existence itself remains, but it is no longer outside the reach of science. It is part of the same story that includes galaxies, atoms, and radiation, linked by the same principles of symmetry, conservation, and probability. This continuity is why the reflections here are not conclusions. They are invitations to think further, to follow where the evidence leads, and to remain comfortable with uncertainty. Physics has shown that beginnings are not absolute, that time itself may be emergent, that balance allows existence without contradiction. What it has not shown is that inquiry ends. The universe remains open, not only in its expansion but in its questions, and so the narration does not close with an ending but with a recognition. The cosmos is something rather than nothing. Physics shows how that can be, but the deeper why remains a frontier, one that continues to inspire study, observation, and thought. The The story of the universe is not finished. It continues with every new measurement, every new theory, and every reflection that arises from wondering about the origin of all things.